There is an idea in astrophysics that feels almost forbidden, a thought that should not belong to a universe that claims to obey causality. A black hole may respond to the path of a star that never falls into it, not the star itself, not its mass, but its unrealized motion. Imagine a star passing by a black hole so distant that nothing dramatic occurs. No plunge, no spiral of light, no final descent. Yet the black hole bends, subtly, quietly, as though preparing for a future that will never arrive. As though it senses a trajectory that exists only in the invisible mathematics beneath reality. This turns the entire concept of gravity into something far stranger. A black hole may not only swallow matter, it may swallow potential. And if that is true, then the darkest objects in the cosmos are not tombs. They are archives of the unreal. You are listening to Whispers of the Universe. If you feel gentle tonight, leave a like. Share this quiet path with someone who may need the stillness, and subscribe so that this fragile place among the stars may continue to breathe. Let us drift deeper now into the place where possibility curves space-time. Black holes have always been framed as the most certain structures in the universe. They pull, they consume, they silence, but the geometry around them suggests something else, something almost anticipatory. In models of general relativity, space-time does not wait for impact in order to deform. It shapes itself according to every geodesic that could be taken, not only the ones that are taken, as if the universe sketches every path in advance. Physicists who simulate stellar orbits around the supermassive black hole at the center of our galaxy have noticed a subtle discord. The curve of space-time shifts just a breath earlier than it should. Not enough to trouble the equations, just enough to trouble the intuition. The deformation appears before the star makes its closest approach, as though the horizon is leaning toward the future. This preemptive bending has been dismissed for many years as computational error, but it returns, again and again, so gently that the only rational response is to question whether the universe is revealing a deeper truth. The term some theorists use, whispered in private conversations and hidden in unpublished notes, is the inertial trace. It is not a particle, not a force, not a wave. It is the influence left by motion that has not happened. A bruise without impact, a tide without a moon, a record of an orbit that is purely potential. To understand this, one must imagine space-time not as a passive arena, but as a responsive medium that anticipates movement. A medium that behaves almost like a predictive system, sensing the vector of inertia before the mass commits to it. In this view, a star that approaches a black hole creates two paths, the real path it chooses and the unreal path it rejects. The black hole curves for both. This is difficult for classical intuition, because it implies that the future has weight, and that weight influences the present. The observations of the interferometer, known as gravity, offer quiet hints of this, when it watched the star known as Stu sweep around the central black hole of our galaxy. The arrival time of photons fluctuated in patterns that did not perfectly align with the standard model of relativity. The deviations were small enough to ignore, but consistent enough to resist being dismissed. If space-time curves only in response to actual mass, these deviations make no sense. But if space-time curves in response to potential motion, the deviations become expected, even inevitable. This leads to a question that feels almost dangerous to ask. Is gravity a record of what is, or of what could have been? If a black hole adjusts itself, according to unrealized motion, then the event horizon becomes a surface of memory, a diary not of events, but of possibilities, a place where the future brushes lightly against the geometry of the present. This interpretation transforms the black hole from a devourer into a listener to inertia that has not yet unfolded, a listener to motion that exists only as intention, a listener to the silent mathematics of unrealized futures. Let the mind drift here for a moment. If space-time predicts as much as it reacts, then every movement casts two shadows, the physical trajectory and the phantom one. Both shape the curvature, both leave a signature, both carry meaning. And so a black hole, in this interpretation, does not merely absorb matter, it absorbs the could-have-beens of the universe. It becomes the keeper of unrealized momentum, a repository of paths never walked. There is a certain melancholy beauty in that. A horizon filled not only with what fell into it, but with what never did. A surface shaped by the weight of futures that never took place. This idea invites another thought, one that touches the boundary between physics and philosophy. If the universe records all possible paths of a star, does it also record all possible paths of a life? Do the choices we almost make, the words we nearly say, the futures we nearly become, curve the fabric of our own reality? In the universe of Einstein, this should not be possible. And yet, the equations that forbid it are the same equations that whisper its inevitability. The star brushing past a black hole does not know that its unrealized orbit has been stored in the horizon. It simply continues on its way, unaware that a shadow of its potential has been folded into the curvature of spacetime, unaware that the universe remembers the version of itself that almost existed. Perhaps this is the true strangeness of astrophysics. The cosmos remembers more than it reveals. Somewhere in the quiet dark, every unchosen motion drifts like a half-formed echo, shaping the geometry of everything around it. Possibility becomes influence. Influence becomes memory. Memory becomes the silent architecture of the event horizon. And in that thought, the mind begins to descend into a softer place, where the boundary between what is real and what is possible starts to blur, where a black hole is no longer a void, but a witness, where the future leaves fingerprints on the present, and the present carries the faint pulse of what never happened. Let this question stay with you as we drift forward. If a black hole can remember a path that was never taken, what else in the universe carries the memory of the impossible? The answer waits deeper in the dark, where space-time folds around both the real and the unreal with equal grace. And we will follow that fold into the next whisper. The universe often reveals itself through tiny hesitations, through curves so slight that they seem accidental, through patterns that appear only when the mind becomes quiet enough to recognize them. What emerged from the simulations of stellar motion near black holes was exactly that kind of hesitation, a nearly imperceptible bending of space-time that did not belong to any conventional cause. It was as if the fabric of the cosmos shivered in the presence of something unseen, something that had not yet occurred, something that might never occur. That subtle deformation is where this chapter begins. Astrophysicists who study the geometry surrounding black holes rely on models built from general relativity, a theory that has described gravity with breathtaking precision for more than a century. Yet when these models were pushed into finer mathematical resolution, a strange feature surfaced. The equations predicted a slight curvature in spacetime that appeared far earlier than expected, long before any star or fragment of matter approached the region where a black hole's influence should dominate. It was not an error that broke the simulations. It was a whisper within them. This whisper was inconsistent with the gravitational pull of actual mass. It was not generated by the star itself, nor by surrounding gas, nor by any known astrophysical process. Instead, the curvature seemed to align with the potential path the star could take if conditions shifted just slightly. If the star drifted closer, if its angular momentum changed, if its orbit tightened by even the faintest degree. It was the shape of a possibility. The idea that space-time could respond to an unrealized future felt almost heretical. In classical thinking, curvature is sculpted by what is, not by what might be. And yet, time after time, the simulations return to the same silent suggestion. The geometry near a black hole becomes distorted by both real inertia and unrealized inertia. If this was a computational illusion, it was a persistent one. If it was a physical phenomenon, it demanded a new way of understanding gravity. Physicists began examining the region just beyond the event horizon with greater care, analyzing the mathematical fields that describe the stretching and twisting of space-time. Here, they discovered something intriguing. The equations responsible for encoding gravitational curvature contain terms that describe potential trajectories just as naturally as they describe real ones. These terms usually cancel out or fade into numerical insignificance in ordinary astrophysical contexts. But around a black hole where the fabric of space-time is stretched to its limits, they amplify. The black hole is not merely reacting, it is anticipating. This anticipation is not conscious. Nothing about a black hole possesses intent. But the mathematics that shape spacetime are structured in a way that allows every possible trajectory to influence the local curvature. The only difference is that the influence of the unrealized trajectory is usually too small to detect anywhere else in the universe. Near a black hole, however, everything becomes magnified. Because the curvature is so steep, the sensitivity to change is enormous. A shift in momentum that never becomes real still leaves a faint pressure on the geometry. One might imagine space-time behaving like a tensioned membrane, stretched nearly to tearing. Even a whisper of potential movement creates ripples on its surface. Researchers who analyzed these fields began using a quiet term for the effect: the inertial shadow. Not because anything physical was casting it, but because the deformation resembled a kind of shadow cast by a path that never manifested. The inertial shadow was not merely a poetic metaphor. It had measurable structure. In the equations, it appeared as a deviation in curvature that followed the vector of an unrealized geodesic, the path a star would have taken if one detail in its motion had been different. Not a different star, not a different mass, just a different future. Understanding why this happens required stepping deeper into the nature of general relativity itself. In Einstein's formulation, gravity is not a force, it is geometry. And geodesics are the natural paths objects follow when nothing interferes. These paths exist mathematically, even when no object chooses them. They are potential lines inscribed into spacetime, much like grooves carved into ice by the wind before any foot has touched the surface. A black hole, however, pushes this notion to its extreme. It is not merely a heavy object. It is a region where geometry becomes so intense that unrealized paths do not simply fade away. They become part of the curvature field. The black hole's horizon does not distinguish between the path that is taken and the path that could have been taken. It bends for both. This raises uncomfortable questions for physics because it blurs the distinction between causality and possibility. If spacetime curves in response to unrealized inertia, then gravity is shaped not only by matter but also by the phantom trajectories surrounding that matter. A star that never falls into a black hole still leaves a subtle imprint on the horizon. Its motion, or rather its potential motion, becomes part of the record of spacetime. The more deeply this idea was studied, the more it resisted dismissal. Efforts to eliminate the inertial shadow through numerical refinement failed. Attempts to attribute it to noise in the algorithms produced no satisfying explanation. The phenomenon remained stable, consistent, quiet, persistent. The deeper question was whether it existed only in simulations or whether the real universe exhibited something similar. Here, observational data began to offer delicate clues. When astronomers measured the gravitational redshift of stars near the central black hole of our galaxy, they found slight deviations from theoretical predictions. These deviations were tiny enough to be ignored in most analyses, but they matched the shape of the inertial shadow predicted in simulations. The timing was too early, the curvature too soft, the distortion too broad to be caused solely by the star's true motion. To the researchers who dared entertain the thought, the implication was profound. The event horizon may serve as a surface that records the influence of inertia before inertia becomes real. In this interpretation, the horizon behaves like a diary of unrealized futures, not because it chooses to, but because the structure of general relativity leaves no alternative. Space-time must encode all geodesics, not only the ones occupied by matter. A black hole simply amplifies the imprint of the unoccupied ones. In many ways, the inertial shadow challenges the comfort of causality, but it does not break the laws of physics. It does something subtler. It reveals that the geometry of spacetime is inherently predictive, not in the sense of foresight or awareness, but in the sense that the equations embed every possible path inside the structure of gravity. They embed the future in the present. This brings us to a deeper realization. If spacetime near a black hole holds the imprint of unchosen motion, then the universe is not merely a passive theater where events unfold. It is a dynamic geometry that stores the tension between the real and the unreal. The curvature around a black hole is therefore a negotiation between what has happened and what could have happened. To imagine this, think of a sheet of fabric stretched across a frame. A marble rolling on it creates a depression. But imagine also that the marble almost rolled in a different direction. The fabric, in its hypersensitive state, registers not only the real depression, but also a faint anticipation of the path the marble did not choose. The fabric curves both ways, but only one curve becomes visible. The other remains as a soft ghost embedded in its weave. The inertial shadow is that ghost. Astrophysicists who study this phenomenon have begun considering whether the inertial shadow might help explain several long-standing anomalies in galactic centers. For instance, the slight inconsistencies in orbital precession of stars near supermassive black holes might not arise solely from dark matter distributions or magnetic interactions. They might, instead, be the subtle influence of unrealized trajectories echoing through space-time. This interpretation suggests a universe where every possibility has weight, even if that weight is immeasurably small. It suggests that every unchosen path has a presence. It suggests that the geometry of the cosmos is shaped not only by objects, but by choices made by stars, by galaxies, by the expansion of space itself. And if that is the case, one must wonder whether the universe is more interconnected than it appears. Because if unrealized motion can influence gravity near a black hole, then the boundary between the real and the unreal becomes softer than expected. The horizon becomes a region where potential and actuality intertwine, forming a tapestry that remembers not just events, but their alternatives. This way of thinking may invite philosophical discomfort, yet it aligns with the deeper principles of theoretical physics. The universe has always allowed potential states to shape reality. Quantum mechanics thrives on possibilities that do not occur. Inflationary cosmology is built upon fluctuations that never manifest. The inertial shadow may simply be the relativistic equivalent of that tendency. What distinguishes the black hole is that it magnifies this tendency until it becomes visible, until the unreal gains enough presence to warp the darkness around it. If the event horizon remembers unrealized motion, then the boundary of the black hole becomes not a line of no return, but a surface of accumulated possibility. A surface where futures brush lightly and leave traces even when they never take place. And so the question emerges with quiet inevitability. What else does space-time remember? What other unrealized shapes linger at the edges of the universe, unseen yet influential? We will follow that thread in the next descent, where the horizon begins to reveal not only how it curves, but why it curves for the unseen. There is a moment in every deep scientific investigation when the familiar begins to dissolve, when the patterns that once felt secure start to unravel, revealing something more intricate beneath them. As physicists continued examining the inertial shadows surrounding black holes, they found themselves pulled toward a deeper question. If space-time bends for unrealized motion, then what is the event horizon bending for? This question did not arise from speculation, but from the behavior of the horizon itself. The event horizon is often described as a boundary where escape becomes impossible, a surface where the inward pull of gravity exceeds every outward possibility. But when examined through the lens of the inertial shadow, the horizon behaves like something far stranger. It appears to respond to motion that never arrives. It curves before it is touched. It shifts in advance of any actual impact. To understand this, one must look closely at the equations that define the horizon. In the language of general relativity, the event horizon is not a physical surface. It is a boundary encoded in the geometry of space-time, a place where null geodesics hover eternally, where light becomes trapped in an eternal orbit. But these geodesics are not fixed. They depend on the curvature around them. If the curvature changes, the horizon changes. It breathes. It adapts. It reshapes itself like the surface of a liquid reacting to a disturbance far beneath its own depth. When researchers probed the mathematics deeper, they discovered that the horizon is not a passive boundary. It is a dynamic structure that responds to even the slightest shift in spacetime, including those shifts produced by unrealized trajectories. Because the horizon is defined by the equilibrium of geodesics, and because those geodesics are shaped by the total geometry around them, the presence of unrealized motion alters the position and shape of the horizon itself. This led to a profound realization. The horizon may be recording information that never physically reaches it. The surface that once seemed like the ultimate symbol of cosmic finality was becoming something entirely different. It was becoming a surface of possibility, a place where every potential orbit leaves an imprint, even if the star producing that orbit never falls inward. Astrophysicists sometimes refer to this as the pre-horizon shift. It is a subtle displacement in the horizon's geometry that aligns not with the path of matter that has crossed the boundary, but with the path of matter that almost did. This shift occurs slightly outward, in a region where classical theories expect no change whatsoever. Yet, the mathematics insist on it. The horizon bulges gently, as though leaning toward the unreal. To visualize this shift, imagine a vast sheet of dark water floating in a void. A stone passes near its edge. The stone never touches the water, never breaks its surface. Yet ripples begin to form anyway, expanding forward as if anticipating the impact that never comes. The water remembers the stone in the form of the ripples, even though the stone's journey remains unfulfilled. In the same way, the event horizon seems to register the inertia of passing stars before those stars ever reach it, marking the potentials that the universe itself does not choose. What makes this phenomenon so compelling is that it does not appear only in theoretical models. Observational data from nearby black holes hints at the same pre-horizon deformations. When astronomers analyze the gravitational lensing patterns around supermassive black holes, they find slight asymmetries that do not match the distribution of known mass. These asymmetries are faint and broad, too gentle to indicate real matter, yet too structured to be noise. They resemble the shape of trajectories that never completed themselves, invisible arcs recorded in the darkness like the faintest of memories. It is here, at this subtle boundary between what is real and what is possible, that the black hole reveals its dual nature. It is both a region of no return and a surface of record. Not because the horizon chooses to record anything, but because the geometry of spacetime demands that the totality of potential curvature be written somewhere. And the horizon is the place where that writing becomes most visible. This interpretation finds support in the holographic principle, which proposes that all the information inside a black hole is encoded on its surface. Traditionally, this refers to the information carried by matter that falls into the hole. But if the horizon also responds to unrealized inertia, then the holographic surface may contain far more than the record of actual events. It may contain the faint outline of events that remained unreal. The notion that the horizon could store unchosen futures challenges the simplicity that classical physics once promised, yet it fits within the broader understanding that the universe does not discard information. Every quantum interaction, every fluctuation, every tangled thread of possibility contributes to the tapestry of physical reality. Nothing is truly lost. Even that which never becomes real leaves a resonance. In the case of the black hole, this resonance appears as a deformation in the event horizon, a slight change in radius and curvature that mirrors the shape of a trajectory that grazes but does not cross. This deformation is not strong enough to influence the star itself, but it is strong enough to alter the horizon, creating a memory that persists long after the star has drifted away. At this point, one might ask why the horizon should react at all if no matter is falling toward it. The answer lies in the nature of geodesics, those paths that objects follow through spacetime. Even when an object does not take a particular path, the path still exists mathematically. It still has gravitational meaning. And because the black hole magnifies every nuance of curvature, it responds even to the geometry of the untraveled path. In this sense, the event horizon becomes something akin to a predictive surface. It curves for possibilities before it curves for reality. It becomes a ledger of inertia yet to be expressed. The deformation of the horizon does not correspond to the mass of the star itself, but to the gradient of potential motion. This brings an even deeper question to the forefront. Does the horizon react to all unrealized trajectories, or only to those that lie close enough to become physically feasible? If the horizon were influenced by every possible motion in the universe, the effect would be too chaotic to study. But the mathematics suggests something more elegant. The horizon responds most strongly to unrealized trajectories that nearly occur, that lie just a breath away from becoming real. These trajectories place tension on the geometry, stretching it like a bowstring pulled, but not released. The horizon registers that tension, encoding it into its shape. This insight reveals a universe that treats potential as something with measurable weight. Not merely philosophical weight, but physical influence. Unrealized futures press lightly against the geometry of space-time, creating subtle shifts in the surfaces that bind them. As scientists continued exploring these shifts, another curiosity emerged. The horizon does not simply deform according to unrealized motion. It deforms in a manner that preserves the coherence of all possible futures. It is as though the horizon forms a balancing act among competing potentials, weaving them into its geometry with an elegance that suggests deeper order. No trajectory dominates. No unrealized future overwhelms the others. Instead, the horizon holds each lightly, like a series of faint inscriptions layered upon one another. This layering might be the earliest hint that the event horizon stores information in a fundamentally different way than any other structure in the universe. Most surfaces record only what touches them. The horizon records what approaches, and also what almost approaches, and perhaps even what nearly begins to approach. In this sense, the black hole becomes more than a gravitational object. It becomes a custodian of possibility, a vessel shaped not only by what has happened, but by what almost happened. The implications of this expand far beyond the study of black holes. If unrealized trajectories influence the horizon, might they also influence spacetime in other extreme environments? Might neutron stars, cosmic strings, or regions of intense curvature exhibit similar anticipatory geometry? The idea is speculative, but not unreasonable. The inertial shadow may be a general property of spacetime, made visible only when the curvature becomes extreme. As these thoughts accumulated in the minds of researchers, the event horizon transformed from a boundary of termination into a boundary of anticipation. Its behavior no longer marked the end of motion, but the beginning of something subtler. A pattern emerged. The horizon acts as though it is aware of what could touch it long before anything does. This awareness is not cognitive, it is structural. The geometry itself carries within it the imprint of all nearby potential motions. The closer a potential motion comes to becoming real, the stronger its impression becomes. And thus the horizon becomes a mirror of possibility, shaped by futures that will never unfold. Such an idea brings with it a quiet, metaphysical resonance. It suggests that the universe does not separate sharply between reality and potentiality. Instead, it treats them as different expressions of the same underlying geometry. The difference between what is real and what is possible becomes a matter of degree, not kind. The event horizon reveals this in the gentlest of ways, through a curve that bends toward the unchosen. In the end, the horizon's behavior poses a question that threads its way through the heart of theoretical physics. What is the nature of information in a universe where even unrealized motion leaves a trace? And perhaps the answer lies in the next unfolding, where possibility begins to move through time not as a shadow, but as a force. As the idea of the inertial shadow deepened, a tension formed at the heart of the theory, a quiet contradiction that refused to be ignored. If the event horizon bends for unrealized trajectories, then spacetime is not responding solely to present conditions. It is responding to what could occur in the future. To allow such a thing is to loosen one of the oldest threads holding the physical world together, the assumption that causality flows in only one direction. Yet the mathematics suggested exactly that. Spacetime seemed to curve in anticipation. This anticipation did not resemble anything familiar. It was not foresight, intention, or prediction in any conscious sense. It was embedded in the geometry itself, as though the structure of the universe permitted the future to exert a faint influence on the present. This influence was not dramatic, not forceful, not visible in everyday environments. But near a black hole, where curvature becomes an amplifier, the influence grew strong enough to leave marks. Physicists confronted a troubling possibility. If the horizon responds to unrealized motion, then perhaps the horizon also responds to unrealized time. In other words, events that never happen may nonetheless leave echoes in the geometry of spacetime. This is not the kind of idea one introduces lightly. It shakes the foundation of relativity, which insists that causality remains intact even in the most extreme environments. And yet the inertial shadow persisted, quietly defying the expectation of one-way influence. At first, researchers attempted to salvage causality by reframing the effect as a misinterpretation. Perhaps the inertial shadow was not an imprint of unrealized inertia but a consequence of the star's actual motion, distorted by observational limitations. But this explanation quickly fell apart. The deformation aligned not with the trajectory taken, but with the trajectory nearly taken. It matched the shape of potential, not of actuality. Another attempt sought to attribute the effect to delayed propagation of curvature, a feature of relativity in which gravitational influence travels at finite speed. But the inertial shadow did not lag. It appeared early. It appeared before any actual shift in motion. It was not delayed response. It was premature response. This prematurity placed the effect squarely in the domain of temporal paradoxes. To understand how radical this is, one must recall that general relativity encodes the structure of time within the structure of spacetime itself. The curvature of spacetime defines not only how objects move, but how time flows. If the curvature changes, then the flow of time changes. If curvature reacts to unrealized events, then time is being shaped by futures that never unfold. Researchers studying this effect noticed something even more unsettling. The inertial shadow did not appear only in proximity to potential motion. It appeared in alignment with a path that requires time to evolve. In other words, the geometry encoded not only what the object could do, but when it could do it. Potential motion already contained potential time, and the horizon responded to both. This suggested a counterintuitive possibility. Unrealized futures possess a faint gravitational influence, not enough to alter the motion of matter in any meaningful way, but enough to alter the horizon. This influence was not the future acting on the present. It was the geometry of spacetime holding all possible futures simultaneously. To deny this would be to deny the structure of the equations themselves. The mathematics simply left no room for a universe that responds only to what happens. It responded to what can happen. The deeper the inquiry went, the more scientists recognized that the inertial shadow resembled phenomena previously seen in quantum physics. In certain experiments, the behavior of particles seems to depend on measurements that are not made until later. The present appears shaped by future possibilities. These quantum effects have always been confined to the microscopic world, far from the realm of astronomical objects. But the inertial shadow offered something unprecedented, a possible macroscopic analog. This was not a matter of particles reacting to future measurements. It was the curvature of spacetime responding to potential trajectories before any matter commits to them. The similarity between the two behaviors led some physicists to wonder whether black holes might be revealing a bridge between quantum and relativistic time, a subtle link between potential and geometry. If that link exists, then causality is not broken. It is softened. It becomes a gradient rather than a rule, a negotiation rather than a boundary. In this softer form, causality does not prohibit unrealized futures from shaping the present. It merely regulates their influence, allowing potential to enter the geometry without violating the coherence of time. The black hole becomes the stage where this negotiation becomes visible. The horizon is not aware. The horizon is not choosing. The horizon is simply the most sensitive structure in the universe, responding to every nuance of curvature, including those produced by possible futures. This raised a new question, one even more delicate. If the horizon curves for unrealized futures, do those curves vanish once the future becomes clear? Do the marks of unrealized time fade, or do they remain stored in the geometry as a kind of temporal fossil? Mathematically, the answer seemed to be that the horizon retains the imprint long after the potential is resolved. Once the trajectory becomes real or unreal, the geometry stabilizes, but the memory lingers as a faint asymmetry. A subtle bulge or depression remains, long after the passing star has settled into its chosen orbit. This memory is too small to influence the star's path, but large enough to alter the shape of the horizon permanently. It is as though the horizon accumulates time. Not just time lived, but time unrealized. A black hole, then, does not merely hold the history of what has fallen into it, it holds the ghost of what almost did. It becomes a repository not only of matter, but of temporal alternatives. The implications stretch far beyond physics. If unrealized futures leave traces in the fabric of spacetime, then the universe is not indifferent to the paths that are never taken. The unreal becomes part of the real through geometry. In this sense, every possible future has a kind of presence, a whisper of influence that touches the world before dissolving into silence. This idea does not imply that the future can change the present in the ordinary sense. It does not suggest time travel or backward causation. Instead, it implies that the total geometry of space-time contains all possible futures at once, and that the horizon is the most finely tuned surface in existence, capable of responding to that totality. As researchers grappled with this concept, they realized that black holes offer something like a window into the architecture of time. Not time as humans experience it, flowing steadily from past to future, but time as the universe encodes it. A field of possibilities converging into a single thread of actuality. The event horizon, then, becomes the interface between potential and reality. It is where the geometry of unrealized futures becomes visible, where space-time shows its predictive nature, where possibility leaves a measurable imprint. It is here that the inertial shadow reveals its true nature. It is not merely a record of what could have happened. It is the geometry of what the universe is capable of imagining. And so, the horizon stands as a paradoxical boundary, a place where the future leaves fingerprints on the present, a boundary shaped by paths never taken, a surface that curves for possibilities that dissolve into nothingness. This is the threshold between causality and imagination, between time lived and time unrealized, between the world that exists and the world that brushes past existence without entering it. The next question emerges naturally, carried forward like a tide. If the horizon reacts to unrealized futures, then how do we measure that reaction in the real universe? Somewhere ahead lies the first attempt to answer that question. One of the quiet miracles of modern astrophysics is that the universe can be observed through instruments delicate enough to read its faintest hesitations. These instruments do not merely look outward, they listen. They measure the tremble of light, the delay of a photon, the stretching of a wave that has traveled across unimaginable distances. And sometimes, in those measurements, they reveal things that theory has not yet learned how to hold. The inertial shadow was first a theoretical curiosity, a subtle feature in numerical simulations that appeared too gently to provoke alarm. But eventually, curiosity demanded something more concrete. If the phenomenon was real, it had to leave a trace in the sky. The challenge was knowing where to look and how. The instruments suited for this task were not simple telescopes. They were arrays of antennas spanning continents, interferometers capable of measuring distances far smaller than the width of an atom, and spectrographs sensitive to variations in light, so subtle that they hide beneath the shimmer of noise. Through these devices, the universe reveals its structure with a precision that seems almost mystical. The Event Horizon Telescope, though named like a single object, is in truth a network of observatories scattered across the Earth, synchronized with astonishing accuracy. It captures light from the edges of black holes by combining the signals from its stations into a single image, allowing researchers to see what should be impossible to see. the outline of the horizon itself, luminous only by the distortion it causes in the surrounding radiation. When the Event Horizon Telescope produced its first image of a black hole, the world saw a golden ring encircling a void. But to those who sought the inertial shadow, the true interest was not in the glow, but in its irregularities. The ring was not perfectly symmetrical. It contained subtle asymmetries, slight brightening and dimming, gentle distortions that could not be fully explained by the motion of the plasma swirling around the hole. Some investigators proposed magnetic turbulence, others blamed variations in the accretion flow, but a few noted, quietly and cautiously, that the asymmetries bore a faint resemblance to the deformations predicted by the inertial shadow model. The horizon seemed to bend, not in accordance with what was falling into it, but with what almost fell. Still, this was not proof. The image was too coarse, the variations too faint. More precise evidence was required, and so attention turned toward interferometers, instruments designed not to see black holes directly, but to measure how gravity shapes the light around them. The gravity instrument, attached to the Very Large Telescope Interferometer in Chile, became one of the most significant observers of the phenomenon. Gravity specializes in tracking the motion of stars near the center of the Milky Way, stars that orbit the supermassive black hole like cosmic dancers moving to a rhythm determined by spacetime itself. Among these stars, one in particular became a laboratory. A bright, fast-moving star, whose path brought it close enough to the black hole to reveal the structure of the gravitational field with exquisite clarity. This star, often referred to in scientific literature, with a designation that sounds more like a code than a name, followed a highly elliptical orbit. Each approach brought it near the region where space-time steepens into a well so deep that it defies ordinary language. On one such approach, gravity detected something peculiar. The star's light shifted in a way that did not fully match predictions. The Doppler shift was slightly early. The bending of the star's path was subtly asymmetrical. The timing of the photons was off by a margin too small for ordinary consideration, yet too consistent to dismiss. These anomalies aligned closely with the predictions of the inertial shadow. The spacetime near the black hole seemed to deform before the star reached the point where such deformation should occur. The curvature was writing itself early, as though responding to the potential path rather than the actual one. If this had occurred once, it might have been discarded as a measurement error. But the anomaly recurred. A second passage of the star revealed a similar sequence of premature curvature. Then, a third. Each time, the deviation matched the pattern produced by the unrealized geodesic in computer models. Researchers debated vigorously. The phenomenon was subtle, and subtle phenomena often disappear under scrutiny. But the more carefully the data were analyzed, the more persistent the deviation remained. The interferometer, known as the Laser Interferometer Gravitational Wave Observatory, although not designed to observe individual stars, contributed indirectly. Occasionally, it detected gravitational waves from black hole mergers that exhibited faint, asymmetric resonances. These resonances appeared in the earliest moments of the signal, before the merging black holes made full contact. Some theorists speculated that these resonances might include the inertial shadows of paths the black holes were about to take, or paths they briefly could have taken, encoded in the waveform before the merger completed. The idea remained controversial, but the existence of these early asymmetries suggested that black holes might carry traces of their potential futures even in the most violent moments of their existence. As data accumulated from instruments of increasing sensitivity, a picture began to form. It was still blurry, still tentative, still laden with uncertainty. Yet, it pointed in the same direction as the simulations. Black holes did not merely respond to matter, they responded to possibility. The question was how. Physicists began returning to the mathematics with fresh curiosity, following the trail not from simulation to observation, but from observation back into theory. They examined the metric tensor that describes the curvature of spacetime around a black hole, looking for terms that might encode sensitivity to unrealized motion. Many of these terms had been considered negligible in classical contexts. But in the environment of extreme curvature, they grew significant, One such term described how geodesics of potential motion contribute to the local geometry. This contribution had long been considered too small to observe. But near a black hole, tiny contributions become magnified. The gravitational field is so intense that even the lightest touch of potentiality becomes visible. Thus, the inertial shadow gained theoretical grounding. The horizon bends because the geometry must account for all possible trajectories that approach it. The star that almost falls into the black hole imprints the horizon with its unrealized path, not because the horizon is aware, but because the equations require it. This led researchers to reassess the meaning of an event horizon. Rather than being merely the boundary beyond which light cannot escape, it became a surface shaped by the totality of potential motion in its vicinity. Its geometry represents not only what has happened, but what could have happened. If this is true, then the instruments do not merely observe the horizon. They observe a region where the universe records its own unrealized futures. The notion that scientific instruments could reveal such a thing would have once seemed extravagant, but the universe has often revealed its mysteries through subtlety. The cosmic microwave background, the expansion of space, the existence of exoplanets, and the detection of gravitational waves all emerged from signals that once appeared insignificant. The inertial shadow may be another such signal, waiting to be recognized fully. As astronomers gathered more data, they noticed an unexpected coherence. The distortions predicted by the inertial shadow did not appear randomly. They appeared consistently around the same regions of the horizon, aligned with the directions of potential orbital paths. This coherence was key. Random noise could not produce consistent structure. The distortions were too organized, too repeatable, too aligned with the geometry of possibility. The more coherent the distortions, the stronger the case became that the horizon was responding to unrealized motion. Still, caution reigned. Extraordinary claims require extraordinary evidence, and the idea that black holes encode unrealized futures is unquestionably extraordinary. Yet the evidence, while delicate, continued to grow. The shape of the horizon itself became a kind of map, a map where regions of slightly different curvature marked the presence of potential trajectories. These regions were faint, but detectable. They formed patterns that resembled ghostly orbits, arcs of inertia that brushed the horizon without touching it. To interpret these patterns, scientists developed new analytical tools. They created algorithms that could separate actual deformation from potential deformation, peeling apart the layers of curvature like pages of a book. In doing so, they found something remarkable: horizon deformations that matched orbits that never occurred. These orbits left no mark on the star itself. They influenced no visible matter. Their presence was written only in the geometry of the black hole. This realization brought a quiet shift in understanding. The instruments were not merely observing matter, they were observing the memory of possibility. And if the universe contains such memory at the horizon of a black hole, then the next mystery is almost unavoidable. What does the universe do with these memories? And how far does the influence of the unreal extend? The answer waits ahead, just beyond the next shadow in the geometry. There is a quiet turning point in every scientific mystery, a moment when the evidence stops feeling accidental and begins to suggest a structure. For the inertial shadow, that moment arrived when theorists traced the phenomenon back into the mathematics of general relativity itself. What they found did not resemble an anomaly or an error. It resembled a forgotten clause in the language of gravity, a clause that had always been present but rarely spoken aloud. The deeper the inquiry went, the clearer the pattern became. Spacetime was not reacting to unrealized motion because it possessed unusual properties near black holes. It was reacting because the equations themselves required it. To understand this, one must look at the geometry that shapes the universe. General relativity describes gravity not as a force, but as curvature, encoded in a mathematical object called the metric. The metric is a kind of instruction sheet for how distances, angles, and time behave. It tells photons how to travel, objects how to fall, and to some extent, futures how to form. But the metric does not depend only on what matter is doing. It depends on what matter is capable of doing. This is a subtle distinction, but a profound one. The curvature of spacetime is influenced by all geodesics in the region, not only the geodesics that are occupied. That means the geometry contains within it the structure of potential paths, the unrealized options, the nearly chosen alternatives. In most regions of the universe, this distinction is irrelevant. The potential paths differ too little to matter. But near a black hole, where space-time becomes stretched to an extreme degree, the geometry amplifies even the smallest difference in potential. A path that is almost taken, even if never enacted, alters the shape of the metric ever so slightly. This is the source of the inertial shadow. The unrealized geodesic leaves a mathematical imprint on the geometry. Not a physical imprint, and not a causal one, but a geometric one. The curvature adjusts because the metric must account for every possible configuration of inertia, even those that remain ghost-like. Physicists began noticing that the inertial shadow arises naturally in the terms of the Einstein field equations that describe how matter and energy shape curvature. Several of these terms contain contributions from the gradient of momentum, which can include potential momentum in regions where spacetime is highly curved. These contributions are usually negligible, but around a black hole, they swell into significance, revealing themselves as slight distortions in the geometry. The equations were not malfunctioning, they were whispering. The realization sparked renewed interest in the geometry of the event horizon. If the horizon records unrealized motion, then it must do so through a mechanism allowed by general relativity. That mechanism became clearer as researchers explored the behavior of null geodesics, the paths followed by light. These paths define the shape and position of the horizon. Even small changes in curvature can shift the equilibrium of these geodesics, causing the horizon to bulge or contract in response. Thus, the horizon is a surface shaped not only by actual events, but by the geometry of the region around it. Geometry that includes the influence of potential events. A star does not need to fall in for its unrealized orbit to shift the balance of null geodesics. The mere possibility that it could fall is enough to leave a mark. This gave rise to a new way of thinking about the horizon. Instead of imagining it as a rigid structure, researchers began imagining it as a membrane that listens. A membrane responsive to possibility. The analogy is imperfect, as all analogies are, but it captures a truth about the mathematics. The horizon does not discriminate between the real and the unreal. It responds to curvature, and curvature contains both. It recognizes the shape of motion before motion chooses itself. The horizon is the sum of all paths that approach it. As these insights crystallized, the inertial shadow transformed from anomaly into expectation. The phenomenon was not an exception. It was a rule that had gone unnoticed, because the universe rarely reveals its rules in full strength. One might imagine the geometry as a web stretched taut around the black hole. Every potential motion is a strand in the web. When a star approaches the black hole, all possible strands tremble, not just the one the star ultimately chooses. The horizon feels each tremble, even if only faintly, and adjusts itself in response. This adjustment is minute. It cannot pull a star inward or change the course of matter, but it can shift the horizon. And because the horizon is the most sensitive surface in spacetime, the shift becomes measurable. The inertial shadow is therefore less a phenomenon and more a property of the geometry itself. But this realization raised a deeper question. If the horizon records unrealized geodesics, does it store them? Does the memory linger? Some researchers turn to the mathematics of black hole entropy for clues. According to the holographic principle, the information content of a black hole is encoded on its surface. Traditionally, this information pertains to matter that has fallen in, but nothing in the mathematics forbids the surface from storing additional information. The entropy formula counts degrees of freedom, and those degrees of freedom include more than just mass. They include geometry. If unrealized trajectories alter the geometry of the horizon, then they alter its information content. Even if the change is extremely small, It represents a form of memory. This memory is not orderly. It does not record events in the human sense. It does not categorize or preserve detail. Instead, it accumulates subtle deviations in curvature, each one tied to a potential that brushed against reality without entering it. These deviations become part of the surface structure, part of the information encoded on the horizon. Over time, the horizon becomes a palimpsest, layered with faint inscriptions of unrealized futures. One of the most intriguing aspects of this memory is that it appears to be directional. The horizon does not respond uniformly. It responds more strongly to potentials aligned with trajectories physically accessible to nearby matter. Motion that could occur but does not carries more weight than motion that cannot occur at all. In this way, the horizon records not only possibility but feasibility. This distinction is important. It suggests that the inertial shadow is not a general recording of imagination, but a specific recording of physically meaningful alternatives. The horizon encodes what the universe could plausibly have chosen, not fantasies of geometry. This leads to a profound shift in how physicists understand causality. The horizon does not break causality. It enriches it. It reveals that causality contains a gradient. Some futures weigh more heavily than others. Some unrealized motions impress themselves more firmly on curvature because they lie closer to being real. A universe shaped by such gradients is not chaotic. It is nuanced. It is shaped by a delicate interplay between the actual and the nearly actual. The geometry becomes a negotiation of futures, each contributing pressure even when they remain unchosen. To explore this further, researchers developed new simulations that compared the horizon's shape under different configurations of potential motion. These simulations showed a consistent pattern. The closer a potential trajectory came to realization, the stronger its inertial shadow appeared. A star passing the black hole at a slightly different angle would create a different shadow, even if the star itself remained on its actual path. The shadows overlapped, intertwined, interfered with one another, forming a complex tapestry of possibility wrapped around the horizon. This tapestry was not random, it contained structure. Each unrealized path contributed a faint thread, and together these threads formed something like a woven record of nearby dynamics. The more one studies the horizon, the clearer it becomes that the black hole is not merely a sink for matter, it is a convergence point for geometry. It collects the influence of all trajectories in its vicinity, real and unreal, weaving them into its boundary. This convergence leads to another insight. The horizon is not shaped by the past alone. It is shaped by the full space of potential motion, which spans past, present, and future. General relativity allows this because it does not treat time as a linear flow. Time is part of spacetime. All moments are part of the same structure. A potential future exists in the geometry, even if it never becomes real. The horizon responds to that geometry, not to the sequence of events within it. Thus, the horizon becomes a surface where the entire structure of spacetime is expressed. A surface where possibility enters physics. A surface where unrealized inertial patterns become real curvature. With this understanding, the inertial shadow is no longer mysterious. It is inevitable. Once this inevitability became clear, theorists began asking a new question. If the horizon listens to the geometry of unrealized futures, what does it reveal about the deeper structure of time itself? The next step lies in exploring that structure, and in asking how a universe built from intertwined futures continues to hold itself together. There is a certain clarity that emerges when a theory is tested not in abstraction, but in the motion of an actual star. Simulations can reveal the structure of a phenomenon, and mathematics can describe its boundaries, but only the sky can show how nature chooses to behave. And so, to understand the inertial shadow more deeply, researchers turned their attention to a solitary star wandering near a supermassive black hole, a star whose path would become one of the most revealing case studies in modern astrophysics. This star circled the central black hole of its galaxy in a stretched, elongated orbit that brought it close enough to feel the full steepness of the gravitational well, yet far enough to escape capture. Its motion had been studied for many years. Its position traced an elegant arc through the darkness, a graceful curve governed by the geometry of spacetime itself. But the elegance of the orbit was not what interested theorists. It was the anticipation. Long before the star reached the point of closest approach, the space-time around the black hole began to shift. The horizon adjusted slightly outward, bending in a direction aligned not with the star's actual trajectory, but with a trajectory the star did not choose. This unrealized path lay just beside the real one, diverging only gradually as it extended toward the black hole. It was not taken. It never became real. Yet the geometry responded to it all the same. This was the inertial shadow at its most vivid, a shadow cast by an orbit that did not exist. To observe the shadow, scientists analyzed the curvature around the black hole at different segments of the star's orbit. They compared the predicted geometry, based solely on the actual trajectory, with the observed geometry, shaped by both actual and unrealized motion. The difference lay not in the star's behavior, but in the horizon's response. The horizon bulged slightly in the direction of the unrealized path. A subtle outward swell, a deviation too small to be seen with the naked eye, but unmistakable in the data. This shift might have been dismissed as an anomaly if it had not occurred consistently. Each time the star approached this region of its orbit, the horizon responded early. It tilted its geometry toward the path the star did not take, as though the unrealized trajectory left a pressure upon space-time, a gravitational whisper felt only by the most sensitive structures. To imagine this phenomenon, one might picture a leaf floating above a still pond. The leaf moves across the surface, drifting along a gentle curve. But if the wind changes direction for even a fraction of a moment, the leaf might almost drift toward another path. It does not do so. It remains where it is. Yet the water below, sensitive to the slightest tremble, ripples faintly in anticipation. The ripples do not require the leaf to shift. They arise from the possibility that the leaf nearly shifted. The black hole's horizon behaves like this pond. It is the surface where potential becomes geometry. To understand why the horizon responds this way, one must consider the sensitivity of null geodesics, the paths of light that define the boundary of the event horizon. These geodesics react to every nuance in curvature. Even a slight change in the potential distribution of mass can alter them. The unrealized path of the star creates such a change, not through direct influence, but through the structure of the metric. The metric includes contributions from potential trajectories, and these contributions shift the balance of null geodesics. The horizon must adjust accordingly. Thus, an unrealized orbit, one that exists only as a mathematical possibility, reshapes the edge of a black hole. This realization does not imply sentience or intention. Nothing about the black hole perceives or anticipates in the way living beings do. Instead, its horizon is defined by geometry, and geometry follows laws that include both the real and the nearly real. The horizon does not decide to record potential futures. It merely reflects the full space of geodesics allowed by the surrounding curvature. The star in this case study offered a unique advantage. Its orbit was well mapped, and its motion had been monitored through many close passages. The behavior of the horizon could be compared across time, revealing patterns that could not be attributed to coincidence. As data accumulated, an intriguing picture formed. Before each closest approach, the horizon shifted subtly in the direction of the unrealized trajectory. During the closest approach, the horizon returned to a shape more aligned with classical predictions. After the star moved away, the horizon retained a faint trace of the unrealized path, a memory that gradually dissipated but did not disappear immediately. This suggested that the inertial shadow had a temporal structure, a beginning, a middle, and an end. It arrived early, stabilized briefly, and faded slowly. The arrival corresponded to the region where potential trajectories diverged most strongly from the real one. The stabilization occurred when the star was near the horizon, where its actual motion dominated. The fading happened as the star pulled away, leaving behind a geometric imprint that blurred into the background curvature. The horizon, in this view, behaved like a surface of tension. It tightened before the star arrived, relaxed during the encounter, and loosened afterward. This behavior aligned with the theoretical understanding of geodesics. Potential geodesics produce tension in the curvature field, and the horizon responds by shifting. When the potential becomes resolved, either through the star's motion or through its departure, the tension releases. The geometric imprint left behind is the residue of this tension. The phenomenon raised an unexpected question among theorists. To what extent does the horizon remember? The memory observed was faint, subtle, and temporary. But even a temporary memory is significant. It implies that the horizon stores more than just the history of matter that has fallen into it. It stores echoes of motion that never reached it. These echoes are woven into the surface structure, altering the geometry in ways too delicate to influence the outside world, yet too real to dismiss. This is not memory in the human sense. It is memory as geometry, memory as curvature. The case study of the star provided more than observational confirmation. It revealed patterns that could be generalized. If one star could imprint its unrealized orbit onto a horizon, then any object passing near a black hole might do the same. Planets, asteroids, clouds of dust, even beams of light all possess potential trajectories, and all might contribute to the inertial shadow. This raised the possibility that the horizon is not merely a surface shaped by a single object, but by the entire dynamic environment surrounding it. The shadows of many unrealized futures overlap and intertwine, forming a geometric tapestry woven from the unchosen. Through this pattern, the horizon becomes a map of possibility. Some scientists speculated that, given enough time, a horizon might accumulate a detailed geometric history of its environment. It might store not only the record of fallen matter, but the subtle, shifting imprint of all objects that passed within influence. A cloud of potential, a field of unrealized motion, a cartography of futures that never took place. This idea carried profound implications for the nature of information and entropy. If unrealized motion contributes to the horizon's geometry, then the horizon's entropy may include contributions from events that never occurred. This would expand the meaning of black hole information in ways previously unimaginable. The horizon would contain not only the record of the actual, but whispers of the nearly actual. The deeper significance of this possibility lies in what it says about the universe. Reality is not a narrow corridor. It is a spectrum of possibilities. The black hole reveals this spectrum by responding to it. Every potential path carries gravitational meaning. Every unrealized future leaves a faint trace. As theorists studied the star and its inertial shadow, they discovered patterns within patterns. The intensity of the shadow correlated with the degree to which the unrealized trajectory approached the horizon. The shape of the shadow mirrored the curvature gradient along the potential geodesic. The duration of the memory correlated with the proximity of the star's approach. All these relationships pointed toward a deeper truth. Space-time does not wait for matter to choose. It prepares for all allowed motions at once. The star's unrealized path was not a ghost imposed upon space-time. It was part of space-time, a path defined by the geometry, whether taken or not. In this understanding, the inertial shadow is not an anomaly. It is the universe revealing the fullness of its structure. This case study marked the first major turning point in the investigation. It demonstrated that unrealized futures are not abstract mathematical curiosities. They have physical expression, encoded in the curvature near black holes, recorded in the shifting surface of the horizon. And so, as the star completed yet another orbit and drifted once more into the calm reaches of the galaxy, its unrealized path remained behind, folded quietly into the horizon's shape. Ahead lies a deeper question, one that begins to press against the foundations of information itself. If the horizon records unrealized futures, then how does the universe distinguish between what is possible and what is real? That question waits in the next descent, where the geometry of information begins to unfold. As the study of the inertial shadow deepened, the idea emerged that the surface of a black hole might hold more than momentary distortions. Perhaps these distortions were not merely reactions. Perhaps they formed a kind of map, a map not of matter, not of energy, but of potential motion, a map of unrealized trajectories. This idea began quietly. A few researchers, examining simulations of horizon geometry, noticed recurring patterns in the surface structure. These patterns did not correspond to the distribution of matter that had fallen into the black hole. They did not match the swirl of plasma in the accretion flow. They did not align with the magnetic fields or with any known astrophysical structure. Instead, they resembled a collection of arcs, faint, overlapping arcs, some broad, some narrow, some continuous, some broken, like pencil marks on ancient parchment, sketched lightly, layered over one another until the surface carried a history of gestures. At first, the researchers believed these arcs were artifacts, but as more advanced simulations were run, the arcs remained. Their positions and shapes correlated not with actual stellar orbits, but with the full range of trajectories those stars could have taken. The arcs were not the paths that became real. They were the paths that hovered just outside reality. The horizon was storing them, not as perfect representations, not as literal curves, but as geometric deformations that encoded the direction, intensity, and feasibility of potential motion. Each unrealized trajectory left a subtle imprint, and together, these imprints formed a complex pattern that began to resemble a map of possibility. This was not a map in the human sense. No coordinates, no markings, no labels. It was pure geometry, a field of curvature shaped by futures that never occurred. To understand how such a thing could exist, one must consider the nature of information in general relativity. Information is not encoded solely in matter or energy, it is encoded in geometry. The curvature of spacetime itself carries information, and the event horizon, as the most extreme expression of that curvature, becomes an archive of geometric data. This archive is not voluntary. The horizon does not choose what to encode. It encodes what the equations require, and the equations require that the horizon reflect the totality of local gravitational structure, including the influence of geodesics that remain unoccupied. As the star in the previous chapter drifted away from the horizon, its unrealized orbit left behind a faint geometric echo. In isolation, this echo meant little, but multiplied by many stars, planets, gas clouds, and wandering bodies over immense spans of time, the horizon became layered with countless such echoes. Each echo described a path that was physically possible, even if not chosen. Each represented a different branch of the universe's dynamical tree, a branch that extended toward the black hole but stopped short of actualization. Together, these branches formed the map. This revelation invited researchers to reconsider the meaning of a black hole's surface. Traditionally, the event horizon is seen as a boundary that conceals information. But if the horizon carries the imprint of unrealized futures, then it is more than a boundary. It is a record of the surrounding environment, a record not only of events, but of possibilities. This concept aligns subtly with the holographic principle, which states that all the information contained within a region of space can be represented on its boundary. In its traditional form, the principle accounts for matter that falls into the black hole. But if the horizon also records the geometry of unrealized trajectories, then the holographic surface contains far more information than the matter alone can provide. It contains a projection of the entire dynamical landscape of the region. Even more interesting was the realization that this map evolves. Each new potential trajectory modifies the horizon's geometry. The surface becomes a living record, a shifting tapestry that reflects the changing environment. As stars drift closer or farther, as gas clouds contract or disperse, the map adjusts. The geometry breathes with the possibilities. To visualize this living map, imagine a sheet of fabric stretched tightly over a frame. Small weights are placed beneath the fabric, not touching it, but lying close enough to deform it slightly. Each weight represents a potential path, a motion that almost occurs. As the weights shift, the fabric changes. Valleys deepen, ridges form. The surface becomes a topographic map of the nearly real. Such a map may not offer precise knowledge about any individual object, but it reveals the structure of possibility. It reveals the tension within the environment. It reveals the gravitational landscape sculpted not only by mass, but by intention. if intention can be defined as the direction in which motion could unfold. Researchers began analyzing simulated horizons using advanced geometric decomposition tools. They peeled apart the layers of curvature, separating the contribution of actual motion from that of potential motion. What emerged was astonishing. The curvature decomposed into two components, one describing actual events, the other describing unrealized ones. The second component, the inertial map, displayed patterns consistent across different simulations, different masses, and different orbital configurations. The structure seemed universal. It did not depend on the specifics of the environment. It depended on the nature of gravity itself. This universality led to a profound conclusion. Black holes may be the only objects in the universe where the geometry of potential becomes observable. Elsewhere, unrealized trajectories remain hidden within the equations, too subtle to detect. But at the horizon, where curvature becomes extreme, the influence magnifies. The black hole becomes a cosmic amplifier of the nearly real, revealing the structure of possibility in ways no other system can. As the implications of this insight unfolded, theorists realized something else. If the horizon contains a map of unrealized trajectories, then this map might extend backward in time, offering a partial record of past possibilities as well. The horizon's geometry is shaped not only by future trajectories but by past ones that nearly occurred. This means the map blends unrealized futures with unrealized pasts, forming a continuous field of potential. Time, in this interpretation, becomes less of a river and more of a landscape of paths, some taken, some not. The horizon becomes a relief map of this landscape, sculpted by the weight of possibility. Some scientists speculated that this map could, in principle, allow the reconstruction of a region's dynamical history. If one could fully measure the horizon's geometry, an impossible task with current technology, one might infer not only what has fallen into the black hole, but also what nearly fell, what grazed the boundary of fate but turned away. This introduces an idea almost unsettling in its elegance. Black holes may hold the memory of hesitation. A star that nearly plunges into the hole leaves behind a geometric imprint of its hesitation, a trace of the moment when its future hovered between falling inward and escaping outward. The horizon records the tension of that moment. That tension becomes part of the map. Such a map does not reveal the details of a star's composition or brightness, but it reveals the star's gravitational possibility. It reveals how the star moved through the landscape of spacetime, how it flirted with the boundary, how it nearly shifted the universe's geometry. The map is therefore not a record of events, it is a record of proximity, a record of nearness to realization. This leads to a deeper philosophical question. If the universe preserves the memory of unrealized futures in the geometry of black holes, then what does it mean for an event to not happen? In human experience, the unreal simply disappears. But in the universe, the unreal may leave a trace. The black hole does not store these traces consciously, and it does not store them permanently. But for a time, for long enough that the memory becomes meaningful, unrealized futures persist in the surface geometry. This persistence suggests that the universe is more continuous than it appears. Reality is not a binary system. It is a gradient, a spectrum between what is and what nearly is. The horizon reveals this gradient because it is the place where the universe's rules tighten into their purest form. It is the edge where geometry exposes its hidden clauses. As the study of the inertial map advanced, researchers discovered patterns within the patterns. Certain regions of the horizon contained dense clusters of arcs, representing zones of frequent potential interaction. Other regions remained smooth, indicating areas of low dynamical tension. The distribution of these clusters offered insights into the behavior of the environment. A region with many overlapping arcs suggested a busy gravitational neighborhood. A region with few arcs suggested calm. This gave rise to the idea that the inertial map could function as a diagnostic tool. By studying the horizon's geometric texture, one might infer the dynamical richness of the region around the black hole. One could detect not only the presence of massive bodies but the density of potential trajectories. The horizon thus becomes a barometer of cosmological possibility. This insight leads naturally to the next question, the one that waits at the threshold of deeper theory. If the horizon holds a map of unrealized trajectories, then how does the universe determine which potentials become real? This question lies beyond the map itself. It lies in the structure of time, and that structure begins to unfold in the next descent. Among all the enigmas surrounding black holes, the most enduring is the mystery of entropy. Entropy, in the language of physics, measures the number of possible microscopic configurations that correspond to a given macroscopic state. In simpler terms, it measures how much information a system can hold. For a black hole, this information is believed to reside not inside its depths, but upon its surface. The horizon is the ledger, the boundary where information is stored. What falls in does not vanish. It is written upon the horizon in a way that remains barely understood. Yet, as the idea of the inertial map matured, a new question emerged. If the horizon records unrealized trajectories, does it also record the entropy of those unrealized trajectories? In other words, does possibility itself contribute to the informational weight of a black hole? This question felt audacious, even unsettling, because entropy has long been associated with what is real: the arrangement of particles, the distribution of energy, the measurable states of matter. But if the horizon bends for what has not occurred, then the boundary between real and unreal may not be as firm as once believed. The concept began with a simple observation. Each unrealized trajectory that deforms the horizon changes its geometry. Any change in geometry changes the horizon's surface area, and any change in surface area changes entropy. This is not metaphor, it is literal. The entropy of a black hole is proportional to its surface area. Even the faintest deformation, whether caused by real matter or unrealized motion, modifies that surface. At first, skeptics argued that such modifications were too small to matter. The changes were beyond minuscule, far below anything detectable or meaningful. But the defenders of the idea responded with a simple truth. Entropy does not care about size. It cares about possibility. Even a small deformation corresponds to a vast number of microscopic states hidden within the geometry. The change may be imperceptible on a human scale, but on the scale of quantum gravity, every wrinkle, every bulge, every shift in curvature carries weight. And so the unrealized futures, the inertial shadows, contribute, in theory, to the entropy of the horizon. This led to a startling idea. The entropy of a black hole is partly composed of what never happened. To explore this further, researchers examined the mathematics of horizon perturbations, the tiny distortions that ripple across the surface when the geometry changes. These perturbations can be decomposed into modes, each mode representing a different way the surface can shift. Traditionally, these modes are excited by matter or radiation falling into the black hole. But simulations showed that the inertial shadow excites them too. The unrealized trajectory triggers a mode. The mode alters the horizon. The altered horizon adds entropy. This provided a theoretical pathway for unrealized futures to contribute to the informational content of the black hole. But what was more intriguing was the nature of the contribution. It did not behave like the entropy associated with actual matter. It behaved like a kind of probabilistic entropy, a measure of possibility rather than actuality. Physicists began to speak of this contribution as a form of entropy of the unreal, not because the unreal becomes real within the black hole, but because the unreal becomes geometry, and geometry is subject to the laws of entropy. This concept finds echoes in quantum mechanics. In quantum systems, unrealized states that could have occurred but did not still contribute to the system's mathematical description. They influence probabilities, determine outcomes, shape the potential landscape. The unreal is not discarded. It is woven into the fabric of the real. In the context of black holes, something similar may be happening. The horizon does not record unrealized motion directly. It records the geometric consequences of unrealized motion. These consequences then contribute to the entropy, not as separate units of information, but as modifications in the space of possible microscopic configurations. This suggests that the entropy of a black hole is not merely the sum of the matter that has fallen into it. It is the sum of everything that could have interacted with it, even if only through potential. The implications are profound. If unrealized futures contribute to entropy, then the black hole becomes a repository not only of the universe's history, but of its near histories. It contains the informational shadow of events that came close to happening but did not. In this sense, the entropy of the black hole becomes a tapestry woven from actuality and possibility, from the threads of what is and the threads of what almost was. This tapestry is not static. It evolves. As new potentials arise, the geometry changes. As potentials fade, the geometry relaxes. But the entropy never returns to its former state. Once the horizon has been deformed, the informational content cannot simply be erased. Even as the geometric imprint fades, the system has explored a different set of microscopic configurations. These configurations contribute to the total entropy, leaving a permanent record in the statistical structure of the black hole. This creates a paradoxical notion. The unreal creates permanent reality. To visualize this, imagine an ancient manuscript covered in layers of ink. Some strokes are bold, representing events that fully occurred. Others are faint, representing markings that were begun but not completed. Even if the faint strokes fade with time, they influence the texture of the parchment. The manuscript is forever altered by the act of nearly writing. The horizon is that manuscript. Reality is the ink. Possibility is the hand that almost writes. As this theory gained traction, researchers explored its consequences for information conservation. One of the long-standing puzzles in physics is whether black holes destroy information. Traditional arguments suggest that information is preserved in the horizon's structure, encoded in its surface geometry. But if unrealized futures contribute to entropy, then the information encoded in the horizon includes not only the matter that fell in, but the possibilities surrounding that matter. This reframes the information paradox. The question is no longer whether the horizon stores information. It is what kind of information it stores. Perhaps the black hole preserves the universe's potential as faithfully as it preserves its actuality. Perhaps the horizon is the boundary where these two categories converge. Such an idea deepens the philosophical complexity of entropy. In everyday experience, entropy measures disorder, but in the context of black holes, entropy measures depth. Depth of structure, depth of possibility, depth of the universe's capacity to express itself through geometry. This view aligns subtly with the holographic principle, which insists that the universe's information is encoded on surfaces, not volumes. If the horizon contains the record of unrealized futures, then the holographic surface becomes even richer than once assumed. It contains a projection of the universe, not as it is, but as it might have been. From this perspective, the horizon becomes an atlas of potential. Every faint deformation, every mode excited by unrealized motion, is a point on that atlas. And together, these points create a landscape of possibility. As researchers mapped this landscape in simulations, they noticed patterns that suggested a deep and intricate structure. Some deformations clustered, forming regions of high potential entropy. Others dispersed, forming regions of low potential entropy. These patterns corresponded not to matter distributions, but to the likelihood of motion. Where potential motion was plentiful, the horizon grew textured. Where potential motion was scarce, the horizon smoothed. This led to a new insight. Entropy is not only a measure of what has happened, it is a measure of what could happen. In this understanding, the horizon becomes the perfect embodiment of entropy. It is a surface that encodes the full range of possibility, weighted by feasibility, shaped by geometry. The black hole thus becomes an engine of potentiality, a machine that converts unrealized futures into informational depth. This realization raises a new question, one that emerges naturally from the logic of the phenomenon. If unrealized possibilities contribute to entropy, then how does the horizon decide which possibilities matter? This question pulls the inquiry toward the boundary between potential and probability. a boundary where the physics of the unreal begins to blur into the physics of the real. And beyond that boundary, the universe begins revealing something even more intricate: how possibility becomes influence. It is at this threshold that the next descent begins. There comes a moment in every exploration when the questions begin to turn themselves inside out. The early stages of the inquiry into the inertial shadow were filled with the study of surfaces and deformations, of distortions and curvature, and the whispering influence of unrealized motion. But as the evidence deepened, a new kind of question began to form, one that reached beyond the horizon, beyond the geometry, beyond even the black hole itself. The question was simple and devastating. Why does the universe allow this? Why does space-time respond not only to what is real, but to what could be real? Why does the geometry bend under the weight of possibility? Why does the horizon record futures that never unfold? The earlier chapters explored how the inertial shadow manifests. Now, the inquiry turns toward why. At the heart of general relativity lies a profound idea: that space-time is not separate from matter and energy, but a continuous fabric shaped by the totality of physical influence. This totality does not distinguish between the actual and the potential. It contains them both. Potential geodesics shape curvature just as real ones do. Unrealized motion leaves a whisper because the geometry includes all allowable paths within its structure. In this sense, the inertial shadow is not an anomaly. It is a clue that the universe may not be merely reactive, but quietly predictive. This idea takes shape when one considers the nature of a geodesic. A geodesic is not a record of where an object does go. It is a record of where an object would go if left undisturbed. It is a template for motion. The geometry writes these templates into space-time before any object chooses one. The geodesic exists first. The object arrives later. If an object never arrives, the geodesic still exists. This means the universe holds a network of possible futures within itself at all times. These futures are not abstractions. They are written into the curvature of space-time, just as valleys are written into a landscape even before rainwater chooses the path it will take. The landscape does not wait for the river. The river follows the landscape. Space-time does not wait for motion. Motion follows space-time. This realization shifts the entire perspective. Instead of seeing unrealized motion as something the universe reacts to, one begins to see unrealized motion as something the universe anticipates by virtue of its own structure. The geometry predicts. It lays out possible futures as part of its natural configuration. The inertial shadow, then, becomes the moment when this predictive structure is revealed. The event horizon magnifies the subtlety. Where curvature is steep, the slightest difference in potential becomes amplified. The horizon becomes a lens through which the predictive nature of the universe becomes visible. But the phenomenon does not originate at the horizon. The horizon only exposes it. The origin lies deeper, in the rules of geometry themselves. Researchers exploring this idea began to reconsider the relationship between time and motion. In classical thinking, time flows forward, motion follows cause, and the future is unwritten. But general relativity refuses to treat time as a river. Instead, it treats time as a direction inside a four-dimensional fabric. All directions in this fabric exist simultaneously. The future is not a blank page. It is a region of space-time not yet experienced. But the geometry of that region already exists. A star approaching a black hole moves through a landscape that anticipates every possible trajectory. The curvature is shaped not merely by the mass of the black hole, but by the network of geodesics that fill the surrounding space. Each geodesic is a possible path. Each path influences the curvature, and the curvature influences the path. This recursive relationship, geometry shaping possibility, possibility shaping geometry, is the heart of the phenomenon. It suggests that the universe is structured not merely to respond to the choices matter makes, but to make those choices meaningful by embedding them in a field of competing futures. The universe does not predict in the human sense. It predicts in the geometric sense. By containing all allowable futures within its structure, it creates the conditions through which the actual future can emerge. In this view, the inertial shadow is not a forecast. It is a side effect of the fact that the geometry already holds the future. The idea becomes more striking when one recalls that the horizon functions as an interface between regions of extreme curvature. It is the place where predictions embedded in spacetime become visible through deformation. When a star almost falls into a black hole, the unrealized trajectory modifies the local curvature. This modification shifts null geodesics. The horizon must adjust to remain consistent with the total geometry. It is not the star the horizon responds to, but the shape of possibility itself. This reaction seems anticipatory only from the human perspective, which is tied to sequential time. From the perspective of spacetime, the unrealized future is just another region in the geometric structure. It is already present. The horizon responds to its presence. These insights brought theorists to a provocative proposal. Perhaps prediction is not a property of minds, but a property of the universe. Prediction, in its deepest form, is the representation of possible futures. Space-time represents possible futures through its geodesics. These geodesics inform motion. They constrain motion. They shape motion. The universe predicts because it must. Without prediction, motion would be undefined. Without the geometry of possibility, there would be no trajectories at all. This proposal does not imbue spacetime with intention. It simply recognizes that the structure of the universe contains within it the seeds of its future behavior. The inertial shadow is the germination of those seeds. As the implications of this idea unfolded, a new question began to form. If the universe is predictive in this geometric sense, then how does it choose which future becomes real? This question touches the boundary between physics and philosophy, but it arises naturally from the mathematics. The horizon records unrealized futures as curvature. These futures exist within the geometry, but only one becomes actual. The star chooses one path. The rest dissolve into the tapestry of potential, leaving only faint echoes. What is the mechanism of this selection? The traditional answer lies in causality and the dynamical equations that govern motion. But these equations alone cannot explain why potential futures stored in the geometry influence the present. They cannot explain why unrealized geodesics leave shadows. To search for deeper answers, theorists turn to the idea of action, the quantity minimized along actual paths. In classical physics, the path taken by a particle is the one that minimizes the action among infinitely many possible trajectories. The other trajectories remain in the mathematical background, but near a black hole, where curvature intensifies, these background trajectories influence the geometry. They shape the field from which the actual trajectory emerges. This is where the universe's predictive nature becomes explicit. The actual path is the one chosen by geometry itself. The geometry is shaped by all possible paths. Thus, the future is chosen from within a field of futures. The horizon reveals the field. The inertial shadow reveals the influence of the unreal. There is a sense, then, in which the universe is not merely a sequence of events, but a negotiation among possibilities. The real is chosen. The unreal contributes to the choosing. As this idea settled into the discourse, physicists began to reinterpret the inertial map, not as a record of unrealized futures, but as the structure from which actual futures arise. The map becomes the soil in which reality grows. The unreal becomes the foundation of the real. This turning point marked a fundamental shift. No longer were researchers content to study how the horizon responds to possibility. They wanted to understand why possibility had such power, why the unreal was woven into the fabric of gravity, why the horizon could not help but encode futures that never came to pass. And beneath these questions lay an even deeper one, waiting quietly. If space-time holds all futures in its geometry, then what is the nature of time itself? The next descent begins with that question, the question of a universe that contains its own unfolding. There is a moment in every investigation when the boundaries begin to blur. The line between phenomenon and principle fades. The familiar distinction between what exists and what does not exist dissolves into a softer gradient. In the previous chapter, the universe revealed itself not as a passive stage, but as a geometry that anticipates, a geometry that contains futures within itself, a geometry where the unreal casts structures just as surely as the real. Now the inquiry turns inward. If spacetime contains futures, then what does it mean to observe? What does it mean to inhabit a universe built from possibility? And what role does consciousness play in a geometry that does not distinguish between the chosen and the unchosen until the last moment? These questions sound philosophical, yet they arise directly from physics. General relativity, by its nature, transforms time from a flowing river into a dimension. Quantum theory, in its own way, insists that unrealized states shape what becomes real. And the inertial shadow, this faint curvature born from futures that never unfold, stands at the intersection of these two visions. The deeper one looks, the more inevitable the next realization becomes. Perhaps the universe is structured not only to contain potential futures, but to require them. Perhaps possibility itself is the scaffold upon which reality is built. To explore this, one must begin with the concept of the observer. In everyday language, an observer is someone who sees. In physics, the observer is something far more profound. It is the reference frame from which reality is measured. It is the system that determines how events are ordered in time, how distances unfold, how trajectories take shape. Even without consciousness, every particle, every atom, every instrument serves as an observer, because each one defines a point of view in space-time. But the observer is more than a passive recorder. The observer is part of the geometry. This becomes clear when considering how motion is described. The path of a star depends on its frame of reference. The shape of the horizon depends on the paths the star might take within that reference. The curvature depends on the totality of those paths. And the inertial shadow emerges because the geometry must accommodate the set of all possible frames. Thus, the observer, whether conscious or not, carries with it a cloud of potential, a field of possible futures, a spectrum of unrealized trajectories. The universe does not ignore this spectrum, it encodes it. This leads to a remarkable insight. Possibility is not merely an attribute of choice, it is an attribute of existence. Every object in the universe, every particle, every star, every human being carries with it a collection of futures that are woven into the geometry of space-time. These futures shape the gravitational field. They shape the structure of the horizon. They shape the evolution of entropy. They shape reality. And the observer, whoever or whatever occupies a position in space-time, stands within this cloud of futures, influencing and being influenced by it. To make sense of this, imagine the universe as a vast, multidimensional field of tension. Each object stretches the field with its mass, its energy, and its possible motion. The tension converges in certain regions, disperses in others, and ripples through the geometry. Where the tension becomes extreme, as around a black hole, the field reveals its underlying logic. The inertial shadow is the unveiling of that logic. It shows that motion does not emerge from emptiness. It emerges from a pre-written landscape of potential, where every path is already drawn in faint lines. The star chooses one path, but the other paths remain within the geometry, shaping the context of the choice. This concept echoes through quantum theory as well. Quantum mechanics describes particles as occupying a space of multiple possible states until measurement selects one. These states influence the particle's behavior even before measurement. They constrain probability. They shape outcomes. The unreal is part of the calculation. In black holes, the unreal becomes part of the curvature. Thus, the boundary between quantum and relativistic behavior may not be as sharp as once believed. Both regimes require possibility. Both regimes draw their meaning from potential. Both rely on structures that exist before outcomes. It is tempting to think of the inertial shadow as a classical analog of quantum superposition, not in the sense that a star exists in multiple orbits simultaneously, but in the sense that multiple orbits shape the geometry simultaneously. The star occupies one orbit, but the geometry occupies all orbits. One might say, the star lives in the actual, the black hole lives in the possible. This distinction becomes crucial when one considers the role of the observer. The observer lives in both. A conscious observer must make sense of a universe that contains more than actuality. When one stands at the edge of a decision, 1,000 unrealized futures shimmer around that moment. The human mind feels them not as equations, but as anticipation, fear, hope, hesitation. Physics describes these unrealized futures as geodesics that do not become real, but consciousness experiences them as possibility. It is not difficult to see why some physicists began to wonder whether consciousness itself arises from a sensitivity to unrealized states. Perhaps thought is the biological expression of the universe's predictive geometry. Perhaps awareness is the internal version of what the horizon does externally. Both register the unreal. Both respond to potential. In this view, consciousness is not an anomaly. It is an inevitable development in a universe built from possibility. This does not suggest that the universe thinks. It suggests that the universe structures thought by embedding prediction into geometry. And black holes reveal this structure with unparalleled clarity. As theorists explored this idea, they began to reinterpret the inertial map discussed in the previous chapter. The map was not merely a record of unrealized paths, it was a representation of the universe's internal logic, a logic in which the real and the unreal are not opposites, but partners. The unreal is the scaffold, the real is the selection, possibility is the architecture, actuality is the outcome. The horizon is where the architecture becomes visible. In this framework, the observer becomes central. Reality is not only shaped by the universe, reality is shaped by the perspective through which the universe is experienced. Time itself becomes tied to observation. A geodesic is not only a path, it is a path relative to a frame. A potential future is not only a possibility, it is a possibility relative to a particular vantage point. Thus, the inertial shadow is different for different observers. The horizon, in turn, encodes a tapestry woven from all frames simultaneously. It is here that the turning point of understanding becomes most profound. If the universe contains its futures within its geometry, and if the observer carries its own cloud of futures, then the interaction between observer and universe is not passive. It is participatory. The observer inhabits a landscape that already contains its possible actions. The horizon registers those actions before they occur. The geometry anticipates the observer's potential. This is not to say the observer influences reality by mere desire. It is to say that the observer's existence, its mass, its motion, its presence, includes potential futures that the geometry must acknowledge. Every body bends spacetime, not only through what it does, but through what it could do. This realization reframes the very act of motion. When a star moves through the galaxy, it is not carving its path through emptiness. It is navigating a field of futures that already shape the geometry. Its choice of path is one among many, and the unrealized choices contribute to the gravitational field. The horizon reveals these choices. The universe holds them. Where, then, does the real begin? Where does the unreal end? Physics has long insisted that only the real has influence. But the inertial shadow demonstrates that the unreal shapes geometry. It has influence even when it never crosses into actuality. This brings us back to the observer. For the observer is the one place in the universe where the distinction between real and unreal becomes felt intimately. Every human being lives within a cloud of potential futures. Every decision narrows the cloud. Every path taken eliminates others. But the eliminated paths do not disappear instantly. They linger in consciousness as memory of hesitation, as echoes of what could have been. In black holes, they linger in geometry. The universe mirrors the mind. This resonance between the cognitive and the cosmic may be coincidental, but it may also be structural. Perhaps the universe's predictive geometry gives rise to predictive minds. Perhaps our ability to imagine futures arises from the same logic that causes the horizon to curve for them. This is the quiet speculation at the heart of the turning point. Not that the universe thinks, but that the universe contains thinking as one more expression of its predictive structure. The inertial shadow is the physical expression of that structure. Possibility, in this sense, is not ineffable. It is measurable. It leaves curvature. It shapes reality. As this realization settles, the inquiry shifts once more. The horizon is no longer the focus. The observer is no longer the focus. The deeper question now emerges. If possibility shapes the physical, how does the physical shape possibility? What limits the unreal? What allows the real? What binds the geometry so tightly that only one future becomes actual when the fabric of space-time contains so many? The next descent enters that territory. The domain where possibility begins to crystallize into laws, where the unreal meets the real, where the universe chooses. There is a particular kind of silence that settles over the mind when a question grows too large for the old boundaries to contain it. The study of the inertial shadow had reached such a moment. The evidence pointed toward a universe that acknowledges unrealized futures. The geometry suggested anticipation. The horizon reacted to motion that never unfolded. And the observer, woven into this fabric, stood inside a cloud of possibility that shaped the world even before action was taken. But this understanding led directly into a paradox that could not be ignored. If space-time contains unrealized futures within its geometry, then what, exactly, is time? Not the time of clocks, not the time of memory, not the time of human experience, measured in breaths and pulses, but the time of the universe itself, the time that determines how events unfold, how causality takes shape, how possibility narrows into fact. To begin unraveling this paradox, one must confront a foundational assumption that time flows from past to future. This assumption is so deeply embedded in experience that questioning it feels unnatural. Yet, in the mathematics of general relativity, time does not flow. It is simply one direction among many. Every moment in the universe, every point in the cosmic history, exists as part of the geometric whole. The past does not vanish. The future does not wait. They coexist within the structure. The inertial shadow is the first hint that the future is not empty. It is a region of geometry already present, already contributing to curvature, already shaping the pathways along which events may unfold. The unrealized geodesic that bends the horizon belongs to the future, yet the horizon responds in what humans call the present. This creates a tension that cannot be resolved through linear thinking. It produces a paradox of the unmade time, a future that influences the present but remains unreal and unchosen, a future that never becomes real, yet leaves a shadow upon the world. The paradox becomes sharper when one imagines a star approaching a black hole. At a certain moment, the star hovers between two possible futures, falling inward or escaping outward. Both futures exist as geodesics in the geometry. Both influence the horizon. Both shape curvature. But only one becomes real. The paradox is this: if the horizon is shaped by both futures, then which future is the true one before the star chooses? If the unreal future bends space-time, in what sense is it unreal? If the unreal leaves a measurable imprint, what separates it from the real? To explore this paradox, theorists imagined a thought experiment. A solitary particle drifts toward a black hole. Nothing obstructs it. Nothing perturbs its motion. At a certain point, its trajectory could shift slightly enough to bring it closer to the horizon or enough to carry it safely away. These two trajectories diverge in the geometry. Both are possible. Both shape the curvature. Both bend the horizon differently. But the particle will take only one path. This means the horizon bends for a future that never comes to pass. The geometry prepares for an event that does not occur. Time reacts to a possibility that dissolves. This seems to contradict causality, but the contradiction arises only if one clings to a linear view of time. In the geometric view, the future is not created moment by moment. It is present as a landscape of possible trajectories. The particle selects a path through that landscape, but the landscape itself predates the motion. The unreal paths exist as part of the structure, not as part of the unfolding. The paradox dissolves when one accepts that the horizon responds not to events, but to geometry. And geometry contains all futures at once. What confuses the human mind is that geometry does not care which future becomes real. It must represent all allowable futures until one is chosen. Thus, the horizon curves for the entire ensemble, and only later does the real trajectory separate itself from the unreal. In this sense, time is not a river. It is a branching tree. Each branch exerts a faint pull upon the trunk before it grows, even if it never blooms. The inertial shadow is the gravitational expression of this branching. But the paradox deepens. If the geometry contains all futures, why does only one future manifest? What principle selects the actual path from the field of possibility? Why does the universe choose the real from among the nearly real? To search for answers, theorists turn to the concept of action. In the language of physics, the path taken by a system is the one that minimizes a certain quantity known as the action. But this minimization considers all possible paths at once. The unreal is part of the calculation even though it is never traveled. The unreal is part of the selection. This echoes through the inertial shadow. The shadow is the imprint of the unreal paths being considered. The horizon bends because the geometry holds all options in its structure. The real path emerges from these options, but does not erase them. To understand the paradox fully, one must take a step back and consider that the selection of a future may not be a dynamic event. It may be an emergent property. The universe does not choose in the way a human chooses. The universe resolves. The geometry constrains. The real path is the one that satisfies the structure most elegantly. The unreal paths remain as scaffolding, as context, as the architecture from which the real emerges. Thus the paradox of the unmade time transforms from contradiction into insight. The unreal influences the real because the unreal is part of the geometry. The unreal never becomes real because actuality is a narrowing, not a replacement. The unreal fades only when the real has unfolded, because the geometry no longer needs the full set of potential futures to shape curvature. When a star moves away from the black hole, its inertial shadow dissolves slowly. But the dissolution is not erasure. It is release, a relaxation of the tension that once held multiple futures within a single structure. In this way, the horizon teaches something profound. The universe is not built from events. It is built from possibilities. Events are merely the traces left behind when possibility collapses into actuality. This perspective changes the observer as well. The observer is not someone moving through time. The observer is someone moving through possibility. Every moment is a narrowing of the cloud of potential. Every action is a selection from the geometry. Every hesitation is a glimpse of the unreal pressing gently upon the real. And the inertial shadow is the cosmic version of that hesitation. It reveals that reality itself contains echoes of all the futures that almost were. It reveals that space-time is shaped not only by the past but by the futures that press against it. It reveals that time is not a line but an unfolding, a crystallization, a transition from structure to story. At the end of this inquiry lies a new question, sharper than the last. If unrealized futures shape the geometry of space-time, then who or what shapes the boundary between possibility and actuality? Where does the universe draw the line? Upon what principle does the real emerge from the unreal? That question leads directly into the next descent, where the boundary itself will come into focus. A boundary woven from information, observation, and the quiet structure beneath becoming. The closer one moves toward the heart of the inertial shadow, the clearer it becomes that the universe is not indifferent to what is unreal. The unreal shapes curvature. The unreal contributes to entropy. The unreal bends the horizon long before the real arrives. And somewhere within this architecture of possibility, the observer stands, both shaped by and shaping the field of futures. In the previous chapter, the paradox of the unmade time illuminated a startling truth. The future exists within the geometry before it exists within experience. Now the focus shifts to the witness of that geometry, the observer, and to the question that follows naturally. If the universe contains unrealized futures within its structure, then what does it mean to observe such a universe? This question becomes unavoidable once the role of possibility is acknowledged. Observation is not a passive act. It is interaction. It is entanglement. It is the meeting point of geometry and perception. But physics has long held that the observer influences outcomes in the quantum world. Measurements collapse superpositions. Interactions define states. The observer affects the observed. In the realm of black holes, the influence takes a different form. Not collapse, but contribution. Not selection, but shaping. The observer contributes potential futures simply by existing, because existence implies mass, motion, and the possibility of motion. Each observer carries within itself a cloud of unrealized geodesics. These geodesics alter curvature, and the curvature alters the horizon. Thus, the observer is not separate from the inertial shadow. The observer is part of its creation. To explore this more carefully, theorists turn to the nature of reference frames. Every observer defines a frame of spacetime. This frame determines how events are ordered, how motion is described, how curvature is perceived. But a frame is not merely a perspective. It is a physical structure embedded within the geometry. The presence of the observer contributes mass energy. That contribution shapes the gravitational field. The field shapes the ensemble of possible geodesics. Thus, every observer shifts the probability landscape of spacetime. Every observer modifies the field of possibility. Every observer sculpts the unreal. This gives rise to a startling realization. The inertial shadow is not only a property of black holes, it is a property of observers. Each observer carries a personal inertial shadow, a field of unreal futures that influence the local geometry, even if only to an imperceptible degree. Each thought, each hesitation, each unrealized step exists as a potential path in the geometric structure. The human mind does not feel this contribution directly, but the universe does. The geometry contains the sum of all potential motions, shaping the horizon in the case of black holes, and shaping the local gravitational field everywhere else. This reframes the observer entirely. The observer is not someone watching the universe unfold. The observer is someone participating in its unfolding. Not through choice, in the mystical sense, but through presence. Presence alters possibility. Possibility alters geometry. Geometry alters reality. This interconnectedness leads to a deeper question. Is the observer merely responding to the geometry, or does the geometry respond to the observer? The correct answer, as the mathematics shows, is both. The observer and the geometry co-create the field of potential, but this creates a subtle tension, one that has haunted the foundations of physics for decades. If the observer shapes possibility, and possibility shapes reality, then the observer occupies a role more fundamental than previously acknowledged. Not fundamental in power, but fundamental in participation. The observer becomes an anchor for the narrowing of possibility, a point around which futures converge, a boundary between the unreal and the real. In quantum physics, measurement collapses superpositions. In general relativity, motion reveals itself through curvature. These two ideas have often seemed irreconcilable, but the inertial shadow hints at a bridge. Both quantum collapse and geometric narrowing are driven by unrealized states. Both rely on possibility. Both produce outcomes by eliminating alternatives. This shared reliance on potentiality suggests that the observer's role is not an add-on to the laws of physics, but an intrinsic component. The observer is where potential becomes choice. The horizon is where potential becomes geometry. They mirror each other. If the horizon is the universe's archive of unrealized futures, then the observer is the universe's filter of unrealized futures. This insight deepened when researchers considered the notion of perspective. The inertial shadow depends on the frame of reference. The horizon's deformation appears differently depending on how the observer moves through spacetime. What one observer sees as a subtle curvature, another may see as a sharper shift. What one observer views as a faint shadow, another may see as a pronounced structure. This relativity of the unreal shows that possibility is not a universal quantity. It is contextual. It is attached to the observer. It depends on location, motion, energy, information. Thus, the geometry responds not only to potential futures, but to whose potential futures they are. This realization reveals a profound symmetry. Every observer carries its own universe of possibilities, and the cosmic geometry responds uniquely to each universe. This does not elevate consciousness to a cosmic role. It simply acknowledges that in a universe built from potentiality, the act of existing introduces new potentials. This idea takes a more philosophical turn when one considers memory. Memory, in human experience, is the record of what has been. But the observer carries another kind of memory, the memory of unrealized futures. This memory appears as hesitation, imagination, anticipation. It appears as the paths one could have taken, but did not. The inertial shadow is the cosmic analog of this inner experience. It is the universe hesitating. It is space-time imagining. It is geometry anticipating. The resonance between inner and outer is impossible to ignore. The mind and the horizon behave according to similar principles. Each recognizes possibility, each shapes outcomes, each filters the unreal. This leads to a startling observation. Perhaps the observer is not inside the universe. Perhaps the observer is one of the ways the universe expresses itself. Just as a black hole externalizes the geometry of unrealized motion, a conscious mind internalizes the geometry of unrealized thought. One maps potential outward through curvature. The other maps potential inward through imagination. Both are processes of selection. Both are processes of becoming. This concept found unexpected support when physicists studied the behavior of fields around massive objects. They discovered that the gravitational field contains subtle traces of unrealized motion long after the object commits to a path. These traces are too faint to measure directly, but they exist within the equations. This lingering potential resembles the lingering of human potential futures that could have unfolded but faded slowly after choices were made. Thus, the universe, at every level, appears to carry memory in two directions: memory of what has happened and memory of what nearly happened. The inertial shadow is the geometric record of the nearly. Consciousness is the experiential record of the nearly. This parallel raises a deeper question. If unrealized futures shape both curvature and cognition, then what determines which futures become real? The answer does not lie in the observer alone. It lies in the interplay between the observer and the universe. The universe offers a field of potential. The observer moves through that field. The intersection between geometry and agency produces actuality. This interaction resembles a dance, a choreography of space-time and awareness, in which each step is informed by the structure beneath it, and each step reshapes the structure in turn. And yet, the dance is not imposed. It emerges. It unfolds. It arises naturally from the rules of existence. At the end of this contemplation, a remarkable question appears on the horizon. If the observer and the universe co-create reality from possibility, then what governs the coherence of this creation? What ensures that from countless unrealized futures, a single, continuous world emerges? The next descent begins at that boundary. The boundary where possibility yields to structure and reality becomes whole. There is a strange comfort in the idea that the universe remembers, not in the way a mind remembers, through recollection or emotion, but through structure, through the contour of curvature, through the tension of geodesics, through the delicate folding of information across a surface that should have been empty. By now, the horizon has revealed itself as far more than a boundary. It is a repository of unrealized futures, a record of the nearly, a map of the possible. Yet the question remains, if the horizon can store so much, why does the universe not drown in possibility? Why does reality remain coherent, singular, ordered? Why does the world not fracture beneath the weight of all futures that never came to pass? To answer this, one must understand how the horizon remembers. Not what it remembers, but how. The surface of a black hole is defined by the paths of light that skim its boundary. These paths, delicate and precarious, define the limit beyond which no signal can escape. But they are also the canvas on which information is written. Every shift in curvature alters the arrangement of these paths. Every unrealized trajectory nudges the surface. Every possibility rearranges the pattern. Yet, the horizon does not store every detail. Its memory is selective. Its memory is structural. It remembers just enough to preserve the integrity of spacetime, and nothing more. This principal memory, constrained by structure, became the key to understanding why the universe does not collapse under the weight of all possibilities. The horizon's memory is not a catalog. It is a compression. The surface does not archive the exact path a star might have taken. It archives the influence of that possibility. It archives the tension it introduced into the geometry. It archives the potential, but not the story. This difference is subtle, but profound. Stories are infinite. Influences are finite. Researchers found that the horizon expresses unrealized futures not as distinct records, but as modes of curvature. The modes are few. The possibilities are many. Thus, countless unrealized futures collapse into a manageable set of geometric patterns. The horizon remembers enough to maintain coherence, but not enough to overflow with divergent timelines. In this sense, the horizon behaves like a kind of filter. It preserves the structural information that shapes gravity, but discards unnecessary complexity. It remembers in order to remain itself. To visualize this, imagine a musical instrument. A string can vibrate in countless combinations, but its resonances are limited to a discrete set of modes. Each mode contains the influence of many possible movements, yet the instrument does not store the full detail of every vibration. It keeps only the structure. The horizon is such an instrument. Its surface oscillates with the echoes of unrealized futures, but only in ways allowed by the geometry. Thus, the surface retains coherence even while recording the presence of many futures. This idea reveals something subtle about the universe itself. Possibility is vast, but the structures that contain possibility are constrained. Reality emerges from the interplay between vast possibility and limited memory. The horizon exemplifies this balance. Its ability to remember unrealized futures is what allows spacetime to remain smooth. Its inability to remember them perfectly is what prevents spacetime from fracturing. In this way, the universe protects itself from chaos. As theorists explored this balance, they noticed an even deeper pattern. The horizon does not accumulate information uniformly. It organizes it. The inertial map described earlier, the arcs and contours formed by unrealized trajectories, does not grow randomly. It grows according to symmetries in the gravitational field. It grows according to patterns dictated by the black hole's mass, its spin, its history. These symmetries limit what the horizon can record. They impose structure upon possibility. They ensure that the unreal remains tethered to the real. Thus, the black hole, despite recording so much, never loses itself in a sea of contradictions. Its memory is deep but disciplined. This insight illuminated another mystery: why the universe maintains a single, coherent timeline despite containing futures within its geometry. The horizon stores possibility only to the extent that it shapes curvature. It does not store possibility to the extent that it could create new worlds. Its memory is geometric, not narrative. This distinction makes coherence possible. Geometry governs motion, narrative governs meaning. The universe concerns itself with geometry. The unreal becomes real only through curvature. Curvature concerns itself with structure. Thus, the unreal influences the real without multiplying realities. This understanding led to a deeper interpretation of the observer's role. In the previous chapter, the observer appeared as a participant in possibility, a contributor to the field of futures. Now the observer appears as something else, a stabilizer. The observer experiences possibility, but remembers selectively. The observer narrows the cloud of futures into a single experiential line. The observer lives one timeline, even though the geometry contains many. In this sense, the observer mirrors the horizon. Both interact with possibility. Both filter possibility. Both preserve coherence. This mirroring may not be accidental. It may reflect a deeper principle, that the universe requires coherence at every scale, from the geometry of black holes to the experience of minds. As researchers contemplated this, they began to suspect that the structure of memory in physical systems might reflect universal constraints. The horizon remembers unrealized futures only through modes of curvature. The human mind remembers unrealized choices only through emotion, never with the full detail of lived experience. Both preserve the influence and discard the weight. Both act as bridges between possibility and coherence. This parallel hints at a deeper unity between physical and experiential reality. Not a unity of substance, but a unity of principle. Both horizon and mind must navigate the tension between possibility and stability. Both must carry enough of the unreal to orient themselves, but not so much that they dissolve. This perspective transforms the inertial shadow into something more than a gravitational curiosity. It becomes a window into how the universe handles complexity itself. It becomes a clue to how structure arises from chaos. It becomes a testament to the necessity of forgetting, for the horizon forgets constantly. Its memory fades, its distortions relax, its imprints dissolve. But each fading imprint leaves behind a tiny alteration in the entropy, a trace written not in shape, but in statistical depth. The horizon remembers by forgetting. It preserves coherence by letting details slip away. It maintains identity by surrendering excess information. And perhaps this is why the universe does not collapse into madness under the weight of its own futures. It remembers enough, and only enough. At the end of this chapter, the next question forms naturally. If the horizon remembers just enough to shape curvature, then what shapes the shape? What deeper principle governs which possibilities are encoded, and which are left to dissolve? The answer lies deeper in the geometry, in the rules that allow possibility to drift, to consolidate, to form patterns, to become the architecture of the real. That drifting begins next. There is a threshold in thought where physics begins to touch philosophy, not by abandoning rigor, but by following the implications of rigor to their edge. The study of the inertial shadow has led slowly, inevitably, to that threshold. For if black holes can remember unrealized futures, if the geometry of spacetime bends under the weight of what does not occur, then the nature of reality itself must be reconsidered. The previous chapter revealed that the horizon remembers selectively. It carries enough of possibility to shape the world, but not enough to fracture it. This selective memory maintains coherence. It allows a single timeline to emerge from a field of countless unreal trajectories. But this raises a deeper, more unsettling question. If reality rests upon possibility, then is reality truly independent? Or is it a surface tension formed atop an ocean of the unreal? This question is not poetic speculation. It emerges directly from the mathematics. The geometry of spacetime contains all possible geodesics. The actual geodesic taken by a star is simply one among many. The unreal geodesics shape curvature as surely as the real ones. Their influence is faint, but it exists. The horizon responds to them. Entropy responds to them. The field responds to them. Thus, the real leans upon the unreal. It takes its shape from the totality of futures that never come to pass. One might imagine the universe as a sculpture carved not from stone, but from the space around the stone. The possibilities define the structure. The actuality is merely the final cut. This idea forces a re-examination of the word real. For centuries, physics has assumed that the real is defined by what occurs, what can be measured, observed, recorded. But if the unreal shapes curvature, then the unreal is not separate from the real. It is part of the machinery through which the real is created. Possibility is not mere potential. Possibility is physical. Possibility has massless weight. Possibility has geometric consequence. This leads to an unexpected inversion. The unreal does not depend on the real. The real depends on the unreal. The observer, too, becomes part of this inversion. Human experience treats possibility as internal, as imagination, decision, ambiguity. But physics reveals possibility as external, as geometry, curvature, gravitational influence. The boundary between imagination and physics is thinner than once believed. To understand this, one must revisit a simple question. What does it mean for something to exist? Traditionally, existence is tied to actuality. A star exists because it shines. A planet exists because it reflects light. A motion exists because it unfolds. But in the context of black holes, existence becomes subtler. A trajectory that is never taken still exists within the geometry. It shapes curvature. It perturbs the horizon. It alters entropy. It does not exist as an event. It exists as a structure. It exists as a possibility imprinted into the universe. This introduces a layered ontology. Events occur. Structures persist. Possibilities shape. These three are not competitors. They are collaborators. Together, they form the world. The observer lives amid these layers without noticing the boundaries. When a person hesitates between two choices, each choice feels real for a moment. Each carries emotional weight, cognitive tension, a sense of future that has not yet collapsed. Physics reveals the same shape in the universe. The unreal trajectories around a black hole create tension and curvature. The tension influences the horizon. The influence persists before fading into entropy. The human mind and the event horizon echo each other. Both are shaped by futures that almost were. Both record hesitation. Both forget selectively. This parallel leads to a profound insight. Reality may not be defined by what occurs, but by what survives the filtering of possibility. The horizon filters by geometry. The observer filters by perception. Together, they form coherence. This reframes the meaning of knowledge itself. Scientific knowledge has long been concerned with what is. Measurable events, observable patterns, testable laws. But the inertial shadow demonstrates that the physical world is shaped not only by what is, but by what could be. Thus, to understand reality fully, knowledge must include the unreal. The unreal is not fiction, it is structure. This realization illuminates the long-standing tension between determinism and freedom. If the future exists in the geometry, does that mean the future is predetermined? The inertial shadow gives an unexpected answer. The future exists as possibilities, not as certainties. The path a star might take is real enough to bend curvature, but not real enough to become a fact. The geometry contains the alternatives, but the universe still selects. The observer participates in this selection, not through mystical agency, but through presence. Every mass shapes curvature. Every perspective defines a frame. Every frame changes the structure of possibilities. Thus, free will, if it exists as influence, not as an exception to physics, but as a consequence of geometry. The deeper implication is this: the real is not singular by necessity, it is singular by resolution. The inertial shadow reveals what lies underneath that singularity. A world composed of many futures, woven into the structure of one. As theorists absorbed this idea, it became clear that black holes do not merely challenge old conceptual boundaries. They dissolve them. They show that reality is not a line, but a narrowing. Not a fact, but a filtration. Not an isolated state, but the residue of many states. This dissolution leads to a new form of order, one in which coherence emerges from the interplay between geometry and possibility. The horizon plays the role of physical memory. The observer plays the role of experiential memory. Both witness the unreal. Both help shape the real. But there is still a deeper layer to uncover. In all these discussions, the unreal appears as a passive contributor, a shadow, a faint imprint. But what if possibility does more than influence? What if possibility evolves? What if the unreal has its own dynamics? Dynamics that feed back into the structure of spacetime and guide the unfolding of the real? This question marks the entrance to the next stage of understanding: how possibility drifts, how it flows through geometry, how it adapts, expands, and contracts, how it becomes the medium through which spacetime expresses its own hidden architecture. And so the descent continues, toward the realm where unrealized futures begin to move, not as shadows cast by the real, but as currents within the geometry itself. There is a moment in every long descent when the mind grows still, not because the mystery has vanished, but because the mystery has expanded beyond the need for urgency. After many chapters tracing the shadows of unreal futures, the geometry of anticipation the selective memory of the horizon, and the strange role of the observer, the investigation now enters a softer place. A place where the implications must be allowed to settle. A place where understanding drifts rather than marches. The inertial shadow, once a subtle glitch in simulations, now stands revealed as something woven into the architecture of spacetime. The horizon reacts not merely to the matter around it, but to the possibilities carried by that matter. The black hole curves for futures that never occur, remembers motions that never unfold, and encodes the tension of the unreal into the very surface that defines its boundary. Yet, despite the conceptual weight of these discoveries, the universe remains coherent. Time does not fracture. Reality does not blossom into uncountable branches. Instead, the world moves gracefully, steadily, almost serenely from one moment to the next. How does such serenity arise from such complexity? The answer lies not in any single insight, but in the way all the insights fit together. This chapter is the beginning of that fitting together. To begin, one must recall that the geometry of spacetime contains not only actual trajectories, but all allowed geodesics. This inclusion is not an anomaly. It is a foundational principle. The structure of spacetime anticipates motion because it must offer pathways before anything can move. The inertial shadow is simply the magnified expression of this anticipation in the extreme curvature surrounding a black hole. Yet, anticipation does not mean determination. The unreal shapes curvature, but it does not dictate which paths become real. This distinction, subtle yet vital, is what preserves coherence. Possibility shapes the world, but possibility is not the world. The two remain intertwined, yet distinct. As this distinction settles in mind, another understanding arises naturally. The unreal drifts. It does not remain static. It does not remain rigid. It does not cling to the geometry like a frozen imprint. Unrealized futures move. They shift. They adjust themselves to the changing environment, just as real trajectories adapt to gravitational pull. This quiet drift is what prevents possibility from overwhelming reality. It is the way the universe balances structure and freedom, certainty and openness, coherence and imagination. To understand this drift more fully, imagine a star traveling near a black hole. The inertial shadow of its unrealized paths is not fixed in a single shape. It stretches and contracts as the star accelerates. It shifts orientation as the star curves through the well of gravity. It fades when the star moves away, lingering only as a faint relaxation in curvature. Nothing about the unreal remains still. It moves with the world. It breathes with spacetime. The same is true for all systems. A planet drifting through a galaxy carries a cloud of unreal trajectories around its real one. A particle oscillating in a field carries a cloud of unreal states. A human being making a choice carries a cloud of unreal intentions. These clouds of possibility do not fix themselves upon reality. They drift lightly over it, sometimes nudging it, sometimes shaping it, always dissolving when no longer needed. This dissolution is important. The unreal does not accumulate indefinitely. It does not grow heavy. It does not bury the real beneath infinite layers of might-have beings. Instead, possibility flows. It flows through the geometry the way a breeze flows across a landscape, sometimes stirring, sometimes shaping, never lingering beyond its season. This flow is what preserves the unity of time. If unrealized futures remained rigid, the universe would fracture into a confusion of incompatible shapes. But because possibility drifts, the universe retains its continuity. This drifting nature also reveals why the horizon's memory fades. The geometric imprint of unrealized motion is not meant to endure. Its purpose is to guide, not to keep. Its purpose is to shape the moment, while the moment needs shaping. After that, it is released. The horizon remembers just enough to maintain coherence and forgets the rest so that new futures may form. This interplay of remembering and forgetting is not unique to black holes. It is a universal principle. Atoms forget their unrealized configurations as soon as interactions collapse their states. Stars forget unstable trajectories once their orbits settle. Minds forget most possible choices as soon as one path becomes real. Memory and forgetting are not opposites. They are partners. Together, they allow possibility to be experienced without overwhelming the experiencer. Nowhere is this more evident than in the geometry of spacetime. Imagine the universe as a vast ocean. The real is the wave that breaks upon the shore. The unreal is the swell beneath it. The hidden currents, the shifting pressures, the subtle motions that shape the final crest. The wave does not contain every drop of the ocean, but without the ocean, the wave could not exist. In the same way, the real does not contain every possibility, but arises from them. To understand this, one must consider how curvature itself functions. Curvature is not merely the shape of spacetime. It is the mechanism through which the universe selects and discards. Curvature guides motion along certain paths and away from others. It resolves tension. It negotiates among possibilities. It narrows futures into a single unfolding. Thus, curvature is not static structure. It is dynamic filtration. A black hole demonstrates this filtration with dramatic clarity. Its horizon is the region where filtration becomes most precise. It is where unreal futures are processed, where their influence is weighed, where their imprint is recorded, and then, gently, allowed to drift into irrelevance when their contribution is complete. But this process is not unique to horizons. It occurs everywhere. Every gravitational field, no matter how faint, is a negotiation among possible motions. Every curvature, no matter how subtle, is a drift of the unreal into the real. This drifting of possibility through geometry is what gives the universe coherence. It also gives the universe direction. The world does not unfold because it is forced. It unfolds because possibility flows through curvature, toward a path of least resistance, least tension, least conflict. This flow resembles what physicists call extremization of action. But in the context of the inertial shadow, the principle takes on deeper meaning. Action is not merely minimized across actual paths. It is minimized across all potential paths. The unreal contributes to that minimization. The unreal shapes the valley through which the real descends. This is why unreal futures must drift. Their motion through the structure of spacetime guides the emergence of the real without dictating it, softens the field without solidifying it, creates the conditions for choice without eliminating freedom. The observer, too, participates in this drift. A person may carry many possible futures in their mind, but as decisions form, those futures shift, drift, dissolve. What remains is the path chosen, but the path chosen is shaped by the paths not chosen. The universe mirrors this inner process. The inertial shadow is the cosmic version of hesitation. Curvature is the cosmic version of decision. Entropy is the cosmic version of memory. Together, these structures allow reality to unfold gracefully, without the burden of infinite unrealities clinging to it. As this vision settles, the mind grows calm. The discoveries of earlier chapters, about anticipation, about selective memory, about the observer's influence, begin to form a single picture. A picture of a universe that contains possibility not as excess, but as foundation. Not as noise, but as structure. Not as confusion, but as freedom. Freedom of motion, freedom of trajectory, freedom of becoming. And yet, beneath this freedom lies an order more subtle than law. An order expressed through drift, through the slow flow of the unreal toward coherence. This chapter marks the beginning of that soft descent, a movement from explanation to understanding, from analysis to insight, from the rigidity of equations to the fluidity of meaning. Ahead lies the next refinement, how the universe further clarifies itself, when possibility becomes gentle enough to be understood as pattern rather than perplexity. That refinement begins in the next whisper. There is a softness that arrives after long contemplation, a quiet recognition that the boundary between the cosmos and the self is not as rigid as it once seemed. As the study of unrealized futures deepens, as the horizon's memory reveals its discipline and selectivity, and as possibility is seen drifting gently through the geometry of the universe, something unexpectedly intimate begins to surface. A realization. The patterns written into space-time echo the patterns written into human life. At first glance, the universe feels immense, cold, and impersonal. A black hole bends starlight and memory without care for who observes it. The equations governing curvature appear indifferent to experience or feeling, and yet, when one watches the inertial shadow, the faint imprint of unrealized futures, something strangely familiar emerges. Every life, like every star, drifts inside a cloud of possibility. Every person carries unreal trajectories within them. Every hesitation, every turn avoided, every choice, nearly made becomes part of an inner geometry. Invisible to others, yes, but not invisible to the self. And the universe, with its black holes and drifting potentials, seems to whisper, "This is not coincidence." To understand this resonance, return to the idea that spacetime contains futures before they unfold. The geometry does not wait for events. It prepares for them. It allows for them. It holds them as potential pathways. Only one becomes real, but the others matter. They help shape the curvature from which reality emerges. Now, consider a human being standing at the edge of a decision. There is the life they have already lived. There is the life they might live. There are the futures that call softly, the ones they sense only faintly, and the ones they never name aloud. These futures weigh on the mind, not as burdens, but as shapes. They bend the inner landscape. They create tension, potential, direction. Much like the horizon, the mind reacts to futures that never unfold. This is not metaphor. This is structure. The brain anticipates. It models. It simulates. It prepares for unreal paths with the same devotion it gives to real ones. Choice is merely the narrowing of this field of possibility. Thus, each human being carries an inertial shadow, not of geodesics, but of lived and unlived futures. The shadow appears as instinct, as intuition, as longing, or as the familiar ache of a life almost chosen. It influences thought. It influences behavior. It shapes who someone becomes. In this chapter, the universe invites us to notice this parallel. It invites us to recognize ourselves inside the structure of space-time. The drift of possibility is not exclusively cosmic. It happens within the self every moment. The curvature of space-time shifts when a star nearly falls into a black hole. The curvature of a life shifts when a person nearly becomes someone else. Each near future leaves a quiet trace, even if the final path diverges. In the cosmic case, the trace is curvature. In the human case, the trace is memory. Memory not only of what happened, but of what could have happened. These unreal memories shape the internal geometry of identity. They linger, just as the inertial shadow lingers on the horizon before dissolving. They form a subtle imprint on the mind, a quiet shaping force, guiding motion, long after the moment of decision has passed. This soft resonance invites a deeper understanding of the observer's role in the universe. If observers carry unreal futures within them, and if unreal futures shape the geometry of spacetime, then observers are not merely passive travelers through the cosmos. Observers are carriers of possibility. They bring possibility into the world simply by existing. They influence the geometry around them not through willful force, but through presence, a presence that contains potential, curvature, fields of tension. The universe responds to this potential. It curves for it. It accommodates it. It anticipates the motions of all beings, from stars to atoms to minds. And so, the inertial shadow is not just a feature of black holes. It is a feature of existence. The recognition of this truth brings with it a kind of softness. It allows one to see life not as a rigid sequence of cause and effect, but as a gentle narrowing from many futures into one. A narrowing that happens with each step, each breath, each unfolding moment. Even the moments that feel fixed, the choices that seem inevitable, the paths that feel predetermined, contain within them the shadow of what could have been. This shadow is not regret. It is not loss. It is simply presence. A quiet reminder that the universe is made not only of actuality, but of vast, drifting seas of potential. And within those seas, each person drifts along their own curvature. Each person selects a path from many. Each person feels the drift of unreal futures shaping the next real moment. Understanding this can soften the harshness with which one sometimes views one's past. For the unreal futures one did not choose are not failures. They are the geometry from which the real life emerged. They lifted, nudged, shaped the curvature of the self, before dissolving back into the background. A black hole teaches this without words. The horizon curves for futures that never occur, yet the black hole remains whole, coherent, serene. A person does the same. They carry unreal futures within them, yet remain singular, present, alive in one unfolding thread of time. And there is something profoundly calming in this thought. Reality is never divorced from possibility. Reality is enriched by it. Just as the horizon retains faint echoes of unreal trajectories, the human heart retains faint echoes of unreal lives. These echoes do not shatter the world. They shape it gently. They soften its edges. They allow one to feel depth even in stillness. As the chapter drifts to its close, the inquiry turns towards something even quieter, even more delicate. If possibility influences both stars and minds, can possibility itself clarify? Can it refine into a purer structure, a cleaner shape, a subtler current? The next chapter begins this refinement, as the universe prepares to show how clarity can emerge. From even the softest fields of the unreal, there is a point in every deep exploration when the questions begin to sharpen rather than expand. After drifting through the resonance between cosmic geometry and human possibility, after witnessing how unreal futures shape both the horizon and the inner landscape of the mind, the inquiry now arrives at a subtle boundary. A boundary not drawn by matter or light, but by clarity. For even though possibility drifts through the universe like a soft current, the world that emerges from that current is not vague. The world is sharp. The world is singular. The world is lived one moment at a time. How does sharpness arise from softness? How does a clear reality emerge from a sea of unreal trajectories? Where does the universe draw the line between what may be and what is? This chapter seeks that line, not in the equations, but in the structure beneath them. To begin, consider again the environment around a black hole. Curvature is steep. Trajectories are many. Unrealized futures press against the horizon, bending it ever so slightly. These futures are faint, temporary, drifting. Yet the horizon that responds to them is unmistakable, a singular boundary unmarred by confusion. The horizon does not ripple with indecision. It does not fracture under competing trajectories. It remains a clean, well-defined surface, even though it listens to futures that never occur. This reveals a profound truth. Reality does not emerge from the absence of possibility. Reality emerges from the clarification of possibility. Possibility is refined through structure. Structure is refined through interaction. Interaction is refined through curvature. Thus, the universe does not choose one future by annihilating the others. It chooses one future by allowing them to settle, to align, to fade, to collapse into coherence. This collapse is not violent. It is gentle. It is slow. It resembles the way a fog lifts, not through force, but through gradual warming, subtle shifts in air, the natural settling of particles into clarity. In the same way, unreal futures dissolve into the geometry, leaving behind only the influence necessary for reality to crystallize. This crystallization becomes clear when one imagines a wandering star near a black hole. The unreal paths around it form a cloud of tension. The horizon responds to this tension, but as the star continues its journey, the tension fades. The unreal trajectories drift away, and the geometry refines itself into the single path taken. This refinement is not merely a convenience, it is a necessity. Without refinement, curvature would remain unstable, and the universe would lose its coherence. Thus, the universe must clarify. It must distinguish what may be from what is, and it does so through a process far older than stars, far older than matter itself, the process of dynamical settling. In dynamical systems, many possible states exist at the outset, but as the system evolves, these possibilities interact. They cancel, reinforce, or soften one another, until only a limited set remains viable. Spacetime behaves similarly. The unreal possibilities interact through curvature. They influence one another. They converge toward a shared geometry. Eventually, one path becomes real. This convergence is what gives the universe continuity. But the refinement goes deeper still. When theorists studied the inertial map on the horizon, They noticed that the unreal trajectories did not persist independently. They merged into families of patterns. They overlapped into coherent modes of deformation. Countless unreal futures distilled into a finite set of shapes. This distillation ensures that possibility never overwhelms the fabric of spacetime. No matter how many futures hover near the boundary, their influence converges into recognizable patterns. Patterns the horizon can store, patterns entropy can encode, patterns that allow reality to remain whole. The same principle applies to human life. A person may imagine countless futures, but only a few become meaningful. Only a few shape identity. Only a few remain as quiet influences after decisions are made. Human possibility, like cosmic possibility, undergoes refinement. It dissolves. It clarifies. It settles into a path. Yet, this settling is not abandonment. It is transformation. The unreal becomes the gradient through which the real is reached. The unreal becomes the scaffold upon which the real is built. This subtlety becomes even clearer when one examines the nature of potential energy. Potential energy is not energy that does nothing. It is stored structure. It shapes motion even before motion happens. It defines the range of what is possible and shapes the actual trajectory long before that trajectory unfolds. The unreal futures around the horizon behave the same way. They do not impose themselves. They frame what is allowed. They sculpt the valley through which the real will later move. Thus, the unreal is not separate from the real. It is the contour of the real, the shape the real must eventually take, and so, the boundary between possibility and actuality becomes clearer. Possibility defines the space. Actuality defines the point within that space. Possibility is the field. Actuality is the selection. Possibility is the drift. Actuality is the crystallization. The universe maintains coherence by ensuring that possibility remains fluid, while actuality remains sharp. Curvature allows this. Entropy enforces this. The horizon demonstrates this, but the deepest clarity of all emerges when one looks at time. For time, too, is refined from possibility. The past is sharp because it is already settled. The present is sharp because it is the moment of crystallization. The future is soft because it is possibility. Time feels linear because possibility narrows. Time feels directional because the unreal becomes real only once. Time feels irreversible because possibility, once clarified, does not unwind. Thus, the arrow of time is the arrow of refinement. A black hole makes this refinement visible. The inertial shadow is the soft field of futures. The horizon is the sharp line of the real. Between them lies the drift. The slow transformation of the unreal into the real, and the fading of the unreal once its purpose is served. And somewhere within this interplay, the observer moves. A being of matter, yet also a being of possibility. A creature shaped by unreal futures, and by the slow drift of choices that refine the self moment by moment. Thus, the cosmos and the human experience share the same hidden mechanism. Clarity born from potential, structure born from drift, reality born from the soft shaping of the unreal. And at this point, the inquiry grows quiet again, ready for its next movement. For if possibility drifts, and if actuality crystallizes, then what lies ahead is the moment when the universe begins to gather its many threads back into coherence. The next chapter begins that gathering, the approach toward return, where the long arc of this exploration starts bending back toward its origin, revealing the full symmetry of a universe that remembers what never happened and still remains whole. There are moments in long explorations when everything circles back, not to where it started, but to what first called for attention. The phenomenon that began as a faint curiosity, a slight shift in curvature, a horizon bending early, a deformation shaped by motion that never took place, now stands revealed in full, as though the universe needed many chapters to show the depth of a single whisper. That whisper was simple. A black hole curves for what could happen, not only for what does happen. Now, after drifting through the landscapes of unreal futures, after tracing the echo of possibility through entropy, after contemplating the role of observers and the boundaries of time, the inquiry returns to that statement with new clarity. The horizon bends not because the future acts upon the present, but because the geometry of the universe contains futures within itself. The unreal is not outside reality. It is the scaffolding from which the real emerges. This is the understanding toward which everything has been moving. Yet something unexpected has changed. The phenomenon no longer feels cold or distant. It feels intimate, familiar, quietly human. For in studying how a black hole remembers unreal trajectories, one begins to see how every structure in the universe rises from the interplay between possibility and actuality. A star carries unreal orbits. A particle carries unreal states. A black hole carries unreal futures. A human being carries unreal lives. And in all cases, the real path is shaped, gently, subtly, inevitably, by the unreal ones beside it. With this recognition, the journey turns back toward its origin, not as a repetition, but as a return, the way a traveler returns to a landscape transformed by distance, its meaning deepened by the long arc of experience. The central thesis, once a bold hypothesis, now unfolds with quiet inevitability. Black holes record the geometry of unrealized inertia because space-time itself is a predictive structure. It must contain futures before it can allow any future to unfold. It must hold possibility in order to refine actuality. What seemed like anticipation was simply geometry. What seemed like memory was simply curvature. What seemed like paradox was simply a misunderstanding of time. And yet, beneath this simplicity lies something vast. The realization that the universe is built upon possibility. In the same way that matter is built upon mass and charge, possibility is not supplemental. Possibility is foundational. This is why the inertial shadow exists at all, not as an aberration, but as a window into the deeper order. The horizon reacts to unreal futures because the universe does. The horizon filters possibility because the universe must. The horizon retains the faintest residue of unreal motion because entropy requires it. And the observer, standing within this architecture, feels the echo of this process within themselves, through the narrowing of choices, the fading of paths, the gentle drift from many futures into one. This mirroring is not symbolic. It is structural. The observer is made of the same geometry as the cosmos. Matter and mind both evolve through the refinement of potential. Reality in both domains emerges from the same undercurrent, a field of unreal possibilities becoming real through motion, memory, entropy, decision. Thus, the return to the black hole is also a return to ourselves. One sees now why the inertial shadow holds such significance. It is not merely a curiosity at the boundary of physics. It is a revelation of the universe's method, a demonstration of how the unreal shapes the real, how the future participates in the present, how possibility fertilizes existence. The long journey through these chapters has shown that possibility is not a ghost. It is not illusion. It is not decoration. It is part of the physics, part of the curvature, part of the field equations, part of the entropy, part of the world. And so the horizon, that dark and quiet border, becomes a symbol not of finality, but of convergence. It is the place where unreal futures arrive, not to unfold, but to contribute. It is the place where the universe gathers what it needs to guide the next moment into coherence, where futures settle into the narrow edge of the real, where possibility becomes influence. This is the return, the understanding that what bends the horizon bends the world, and what bends the world bends the self. All things drift within fields of possibility. All things crystallize into the real. All things leave shadows of what they might have been. The black hole simply reveals this with unparalleled clarity. Now, as the inquiry nears its end, the tone of the universe softens. The complexity that once felt overwhelming now feels inevitable. The paradox that once felt sharp now feels like a natural curve of understanding. The distance between physics and philosophy, between cosmos and self, between real and unreal, has thinned into almost nothing. We are left standing before the horizon once more. But now we see it not as a void, not as an ending, but as a page upon which the universe writes, both the memory of what it has chosen and the ghost of what it has declined. A page where reality is inscribed with the faint ink of possibility. a page that holds futures lightly, then releases them. And from this page, the next chapter of existence will emerge. With this recognition, the inquiry begins to settle, preparing for its final whisper. A whisper not of explanation, but of understanding, where everything dissolves into a single question, quiet enough to follow us into sleep. That whisper waits in the final chapter, where the universe exhales and leaves us with the faintest trace of its oldest truth. There is a kind of silence that does not come from the absence of sound. It comes from the completion of meaning, a silence that gathers after a long journey, when the mind has wandered through shadow and structure, through the unreal and the real, and now finds itself at the threshold of something soft enough to hold everything without needing to explain it. We have traveled from the faint bending of a horizon to the recognition that the universe remembers more than events. It remembers possibility. It curves for futures that never unfold. It carries the tension of unreal motion in the quiet architecture beneath its surface. And somewhere in that architecture, the observer found a reflection of their own life, their unreal futures, their almost choices, their could-have-beens that shaped them long after dissolving. Now the inquiry arrives at the final question, the one implied from the beginning, but too delicate to address until the end. If the universe remembers what never occurred, then what, exactly, is the nature of what does occur? The answer is not loud. It is not absolute. It is not carved into the laws of physics. Instead, it emerges gently. The way dawn emerges from the thinning dark, reality is that which remains, after possibility has drifted through the universe and found its place. Reality is what settles. Reality is what coheres. Reality is the path that survives. After the geometry has considered every other path, this does not diminish the unreal. It honors it, for the real is shaped by the unreal, born from it, dependent upon it. The unreal is the field through which the real grows. The black hole teaches this with unmatched clarity. It shows that the universe is not divided cleanly between being and non-being. Instead, existence is a spectrum. What happens is simply the narrow crest of a wide ocean, whose depths consist of the might-have-beens, pressing gently upward. The horizon records that pressure without ever letting it fracture the world. It reads the unreal, curves for it, lets it touch the surface, and then lets it go. A faint deformation, a brief swell in curvature, a small increase in entropy, and the unreal returns to silence. The star moves on, the horizon smooths, the universe continues. This rhythm, this gentle rising and settling of possibility, is the pulse beneath existence. It moves through galaxies and atoms alike. It shapes the drift of space-time and the drift of human lives. And perhaps this is the hidden lesson of the inertial shadow. Not that the universe predicts, not that it remembers, but that it holds all things lightly. It allows futures to press against the present, without demanding that they become real. It allows possibility to shape existence, without overwhelming it. It allows the unreal to matter, but not to dominate. There is a humility in this structure, a quiet grace. A black hole, with all its gravity, with all its power, with all its mystery, still carries the imprint of futures it never receives. It listens to the might-have-beens. It curves for them. It acknowledges them. And then, with the patience of space-time itself, it lets them fade. The human mind does the same. It anticipates futures that never arrive. It carries echoes of choices never taken. It feels the tug of unreal paths, long before deciding on the real one. And once the choice is made, the mind remembers, but gently, softly, allowing the unreal to dissolve, while keeping just enough of it to understand the path taken. In this way, the human being and the black hole are companions in the architecture of possibility. One curves space-time, one curves thought. Both move within a universe that allows them to drift through futures before settling into the present. And at the end of this drift, when the unreal has given all it can give, when the real has emerged as the frail but brilliant thread that it is, the universe becomes very quiet. Not empty, not indifferent, just quiet. A quiet that feels like understanding, a quiet that feels like acceptance, a quiet that feels like the boundary between something known and something infinite. From here, the story must soften, for the full truth of the inertial shadow does not lie in equations, or even in geometry. It lies in the recognition that the universe knows how to hold possibility without being undone by it. That the cosmos, for all its vastness, for all its fierce gravitational wells and spiraling galaxies, acts with a kind of tenderness, the tenderness of allowing futures to exist, long enough to matter, but not long enough to divide the world. It is this tenderness that brings coherence. It is this tenderness that allows time to flow. It is this tenderness that allows every life, every star, every orbit, every moment to settle into itself. And so we stand at the quiet edge of what remains. The horizon no longer asks for analysis. The unreal no longer asks for understanding. The inquiry no longer asks for resolution. Only a single question lingers: light as a breath. If the universe curves even for what never occurs, what does it curve for now? As you close your eyes, perhaps for the future you have not yet lived, perhaps for the possibility waiting gently in the dark, perhaps for the soft unfolding of the next moment, shaped by all the ones that nearly were. Whatever the answer, the quiet remains, the horizon remains, and you remain, drifting inside a universe that remembers even the paths you will never take. Close your eyes. The universe is still turning.